えっと、ちょっと今テスト配信をしようとしているんで、あ、もうできてますね。ちょっと今テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。あ、もうできてますね。ちょっと今テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。あ、もうできてますね。今テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。あ、もうできてますね。今テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。あ、もうできてますね。テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。あ、もうできてますね。テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。もうできてますね。テスト配信を、てか普通に音入ってる。めっちゃ音入ってるわ。できてますね。 お おー。 おーおーおー
My system trouble.テーブル畳んでテーブルに貼りますか。1枚は今ネイキ塚さんのやつです。ここに入れます。下に入れます。塚さんに入れて、今喋ってますが、今のマイクは何が使われてるかっていうと、僕のこれだね、あそこ入り口に今喋ってるんですけど聞こえますか？ちっちゃい、今音声ちょっとでかくしました。これが YouTube に載ってるかどうか。
聞こえるよ。
聞こえますか？あ、よかった。
めっちゃ遅いけど。
まあ遅延があるのは多分よくて、多分今まだ YouTube 上ではこれなんで。
こうやってまだこれ映ってる。なんでこれまだ映ってる？
いや、なんかもう遅延があるんですよ、YouTube って。
こんなに違うの？
ちょっと比較しました。これが YouTube に載ってるの。あ、待って待って。マイクの音結構ちっちゃくなってたんで、ごめんなさい。さっきうるさくなって多分今これで結構いい感じに聞こえてる。もう一回お願いします。
今こんぐらいのラグで聞こえてる。
ラグはいいんだ。ラグはいい。
全部がラグしてる。
てかなんで
こんぐらいの声で聞こえてる。
めっちゃ聞こえるじゃん。
今復活した気がする。
なんか羽ってね。 あれ、それはおかしい。マジそれはまずい。
それはおかしいってこれ聞こえた。
これだ？
今言われたのこれ聞こえた。あ、でもこっちから聞こえなくね、米田の声。
あ、聞こえなかったね。
こっちからは聞こえてないけど、俺らの声、
あ、
会話が。
じゃあ治ったのかな。何も書いてないんだけどな。あれ、なんか怖いな。なんかまた起きそう。すごい怖い。
確かに。あ、ほら、俺らの、じゃあここに置いとくわ。
いや、よくないの。それよくなくて、これ今マイクで音拾っちゃうから、これはぶっちゃう。
あ、違う、今確認用に。
あ、オッケーオッケー。そういうことね。ありがとう。
本番はキスよ、すぐ。
ありがとう。でもめっちゃ音入ってるよ、これ。大丈夫かな。多分治りました。
治った。
ありがとうございます。今喋って大丈夫そう。問題はそうですね。
ポスター一旦待ってもらう感じでいいですか。
Yes, so about the poster presentation, so suddenly the organizer, workshop organizer said it is not good to the inside, right? Yeah, but so the workshop organizer now about to find the magnet for the workshop. Alright. The poster, so I think, yeah, yeah, please wait, so they go by and maybe.
いや、そこにある。
あるから乗っていいよ。
なんならちょっと僕全然いらない。
あ、そう。飲んだ方がいい。
怖いな、これ。怖いな。ちょっと、塚さん一回なんかちょっとプレゼンっぽく適当に喋ってもらっていいですか。
外で聞いてきます。
ガチで怖い。ガチ
ちっちゃくしてるから
あ、いや、多分あれですよ、マイクの音が聞こえ
マイク
ない。それは多分
マイク
僕の
でかくしてもらって
今でかくしたから、ちょっと一応もう一回、塚さん一瞬もう一回喋ってもらっていいですか。
ロボットのデモ動画の方が音が大きい。
まあそれは変えれるわ。
もっとこっちのマイクの音を大きくした方が聞こえやすそう。
あれよマイク
今でかくした。
もともとの音声めっちゃちっちゃいからこれも
いや、今大きくしたんで。
じゃあまた先生
まあいいですよまあたまに岩田君に聞いてもらって調整してくれればいい2人で
確かに別に最悪ここにいる人がさ、普通に聞ければいいので。いや、多分あれかな、ちょっとそこの音をここで拾うのがよくない。僕の声とかで聞こえてると思うんだよ。
どれがの声が出てるし。
だから多分マイクがこいつなんですよ。今ここら辺にあるからマイクの音拾ってるの。ここから出た音がだからまあこの辺の音は聞こえるんですけど、なんかここから来てる音が若干弱かったり。スライドの音入ってて、会場の音がよく聞こえないです。YouTube 上で。
普通に喋ったけどそこのマイクついてここで喋った
で、今のその音の調整をしてました。
Hey, what's the poster board assignment? Can we just put it anywhere?
Oh, you're like inside or outside?
For the Boxy workshop paper.
Yeah, I mean, yes, I know, but so which, maybe there is a specification of inside or outside, right? So,
I don't think it's but
currently actually about the poster inside.
Oh, okay,
So
okay.
Yeah, so about the poster inside
that makes sense. 俺これイヤホンで聞けばいいんだよね。
あ、そうだね。
それで俺とヨネダでもう随時このスマホ聞ければいい。
全然頭が動いてない。
いや回ってないんだよ。ちょっとトラブルが起きて。
ポスターやばいね。
I don't know how long it will be until Yeah, so there is a show that was the copyright AM on
How long it will be until they bring the tape or whatever.
I know, yeah, the vulnerability is outlined, so outside that is
Maybe good.
Maybe good. I hope it works well. So. いや
最悪これに貼る。壁貼れないんだったら。はい。でここのエリアはもう自由に使えて、でこの部屋壁に貼るって話だったらですよ、最初は。ただ今日の朝っていうのに壁の材質的にテープは使わないので。なんで今どこにポスターを
韓国はいつ来られたんですか？昨日ですか？ちゃんと飛行機取れました。東京、はい、昨日の朝10時ぐらい。結局ポスターは今一番出てるじゃん。ヨレガのはどっかに貼れるんじゃない？外に貼る人はもう貼るって感じになったの？それとも
何も分かんない俺は。ちょっとお願いしてるからね。
今動画限定公開もやっちゃってるな。ああ、もしあれだったら全然今俺あれだから使う？
でももう手に死んだ方がいい気がする。
So yeah, about the various open source hardware and its surrounding technologies. And each talk will be 20 minutes, including Q&A, a little short, but you can know a lot of stuff about the open source hardware. Here I want to talk about the advantages and disadvantages of the closed source hardware and open source hardware. The commercial hardware is usually the closed source. For example, the Dimitri Go2. Of course, this kind of the commercial hardware is very sophisticated, but there are several problems, and it is hard to change the hardware. It is difficult to access low-level layers. It is necessary to request repairs if something breaks. But on the other hand, the open source hardware, for example, the CoRL2025, it is easy to modify the hardware. It is free to modify even low-level layers, and it is easy to fix on your own. But why open source robotics? The hardware, I think there are the 4 great points on open source hardware. And the first one is connection. The collaborative research and feedback networks expand by the open source hardware, the regularizing the research community, and also the education. The open source, open access enabled everyone to learn, the creating educational value, and raising the overall technical level. And third one is ecosystem, the reproducible implementation and derivative development are encouraged, allowing technologies to spread across fields and teams, building a strong ecosystem. The last one is very important now, so benchmark. So it will function as a common benchmark, enabling fair comparison and evaluation of different methods and algorithms. Yeah, there are the various types of open source hardware in the world. We can categorize them into the quadruped robot, the bipedal robot or humanoid, the manipulator, or the hand gripper as the manufacturer of the manipulator. So I will show the examples of these categories. The first one is a quadruped robot. Usually they are made of the 3D printed plastic, but sometimes made of metal. For example, the Stanford Doggo, CoRL2025, which will be presented by Thomas. The open quadruped robot, Q, and MEVIUS, which will be presented by me. And the next is the bipedal robot or humanoid robot. For example, the Sigma one at the Robocop circle size, which will be presented by the Gregorio, the Passot, and also the Todrabot, which will be presented by Karen Liu from Stanford, and the Berkeley humanoid ride, which will be presented by QM Liao, and the Duke humanoid from the Boyan Chen, and also MEVIUS from me. And there will be a lot of talks on the open source humanoid robot, because this code is the code held with IGP humanoids now. So yeah, so there are a lot of humanoid robot, open source humanoid robot talks. Also, next one is a manipulator. One of the default standard of the open source manipulator for vision language action models is Aloha. And also SO101 from the Hugging Face is super cheap and is currently used as an open benchmark of visual learning and the vision language action models. And yeah, which will be presented by the Anthony Pione. And OpenARM from NFT is a humanoid-like manipulator for data collection and running. And PAMI2 is a little special there, but the Pneumatic actually the driven open source manipulator. The last one is the hand and gripper. For example, Umi Beat hand, which will be presented by the Kenny Show, and Old hand, which is developed as a course project in the ETH. Also, not only hardware itself, but also the open source software for imitation learning and reinforcement learning is very important for open source hardware development. For example, Isaac Jim and Isaac Shim drastically advanced reinforcement learning and open source hardware, all the open source hardware, and also stable baselines presented by Anthony Laffin. And the robot presented by Anthony Pione, a great platforms for open source hardware. This is almost the last slide, but I think the schedule is not the latest one. But yeah, this is the schedule. But after the opening talk, we will have the 3 invited talks from the Karen Liu, Fiona Liao, and Teseo Ogata. And after that, there is a poster and demo session with coffee break. And then we have we have the 70 posters and inside this room and on the poster board outside this room. And then we have the 4 invited talks. And afterwards, lunch break, and I heard that the lunch box will be provided from the co-organizers. And after the lunch, we have currently 3, but actually now the invited talks become 4, but 4 invited talks, and then the poster and demo session again, and 1 invited talks and the panel discussion afterwards. Also, for the best poster award winners, the open source hardware Reach Mini will be given. However, since the Reach Mini is still under production, the award will not be the actual rocket itself. Instead, the winner will receive the right to receive the Reach Mini once it becomes available. So it's like a voucher. So yeah, this is sponsored by the Hugging Face and the Robot Stacker Kit. So thank you very much for that. Yes, so that's all for the opening talk. So thank you very much for coming today. So please enjoy and connect each other on this open source hardware project. Thank you. Yes, so the first speaker is Professor Karen Liu from the Stanford University. So please, yep, thank you.
Please join.
sharing program that I will switch the presentation of the first invited talk and third invited talk. So the first invited talk now is the Tetsuya Ogata, the professor that was from the Waseda University. So it's about the direct basic course on the open cloud platform for AI developers. Thank you.
Thank you for the introduction. I'm Tetsuya Ogata from Waseda University. Actually, so then, I know the workshop is open source hardware, but now it's an ongoing project. Now we are trying to open this one for the platform to collecting the data for the road foundation models. So first let me introduce myself in short. Now then I'm working on the professor at Waseda University, also the leading some project for the government, supported by the Japanese government for the AI road foundation models. And so also I work on the Moonshot project. It's also supported by Japanese cabinet office, quite a big project. And a long time to work on the intentional learning for the road systems. This is the first works in almost 10 years ago. And then that time I focus on the kind of world model. It can predict the cognitive states on robot itself, and also its posture means that this robot predicts the next poses. That means the robot can generate motion. So now everyone knows this kind of tasks. But it's done almost 10 years ago now. So this is very similar framework on the current imitation learning. So the human operator control the robot and collecting the data. And so the network trying to predict this kind of internal conditions. So pixel motions. So this is a video done at 9 years ago and 7 years ago. So now everyone works on this kind of task unfolding, tower solving process. And in this case, before the generative AI and before the transformers, we use recurrent neural networks, this existing. But in this kind of period, we can show that this kind of demonstration derives and many such kind of exhibitions. And here is one of the works and it connected now also open source hardware. Still not open, but we expect it to be open to this kind of hardware. So you can see almost similar details and our such kind of framework for the dynamics. But it's 8 years old. And we trained this robot for the whole controls by using the imitation learning, end-to-end learning manners for approaching the door and opening doors and the passing doors. And each motion is separately trained in the sense of the mixture of examples of imitation learning frameworks. And finally, it can generate this kind of motion as a whole motion. And it exhibit as an ETC components is the required code that is this kind of memory code. And this is also work done published as Science Robotics 3 years ago, still before the generative AI. But you can see it's robotics works very still. And so this is a kind of collaboration work with the Dutch companies. And I expected them this hardware as an open. So actually this shows that the opening doors and passing doors. But of course this has kind of potential to work on the different types of tasks. So, and after this work, we started the Moonshot project as I mentioned. And we exhibited multiple such kind of demonstration at last year as iCraft in Yokohama. And this robot is also our robot developed on Moonshot, but quite expensive, not so easy to open. But at the same time, we saw the next version of this robot, so this robot, and exhibited the Yokohama and continuing work on the opening passing doors. And now, the latest version we call the IREC based. IREC means an AI-driven robot for infrastructure care. And so you can see, so this one is very easy to control and synchronizing the human operator and sensors and head-mounted display devices. And at the same time, this robot has function that bilateral teleportation. So the human operator easily feels the force feedback from the arms. And so as you can see, this robot can change the height and synchronize many different types of devices for controlling the vehicle and arm grippers. And this is not special robots. So it is open. So I expect it to open arms. Actually, the engineer level is okay. Maybe I will open later for the program. And here is some demonstration done by this robot. Of course, it can do the opening doors and fastening. And also, then, we train the multiple tasking in this kind of demonstration, live demonstration in the end-to-end manner. And here is a scene I use actually exhibited at the conference held in last month. So during 2 weeks, we showed this demonstration over 4,000 times. So with the context of this robot, as I try to connect this one to this activities in the robot association. So it's supported by Japanese companies like this. And this project association aims to the open source foundation model, also open data set. That is one of the important ideas. So that in Japan, so there is not so big company, and there is not big support from the government in the big support from the big carriers. So we need, we think about we need to collaborate with other institutes and universities as a sense of open source, open data source. And as an association, we first collected the data and made some basic foundation models. And I asked some company to use our basic foundation models to for fine-tuning or the original target tasks. And we expected such company to feedback some data from such kind of actual so real applications. And so this is list of the corporate companies in June. So now we about the companies in MEVIUS. And this is you can see there's not so many companies from the industrial robotics. So because this is kind of activity to find a new application based on the foundation model with collaborating such a data set. And this is about the direction. So actually, I'm now chairperson here. And so the important portion is, for example, the Toyota is a very important role to start such robots, many robots for collecting data. And also the television instance now they started collaborating with vehicle intelligence. And there are already some interesting applications for the robot systems with the foundation model in the backyard of the convenience stores. And in this core conferences, we will show the demonstration on October 1st with this one. So this robot is from Toyota companies in the HSR. Actually, this is a standard robot model for the robot at home. And so we will show them this kind of, this actually motion is generated by teleoperations. But some of the university and institutes already use those foundation models fine-tuned by this kind of the data set. So, finally, I'd like to mention a little about why is an ongoing project for the open source business. So, I expected before this workshop, this robot was already open for all of you. But actually, so now we will struggle with such companies. So, as an association, our association, so we, when we contacted Hitachi, so we already mentioned about the possibility to buy these robots. Then the attitude drastically changed. So I think so, especially in Japan, they're still very far from the sense of the open source or open source hardware. So as you know, the industrial robot company in Japan is always very close in the sense of hardware and software. So open source hardware is of course very active and important, but so not only to focus on developing the technology, maybe we need to struggle with such kind of difference of the content, especially
thank you for the presentation. Is there any question from the audience?
I have a question. I have a question to get started. Thank you for your presentation. You showed us some end-to-end demonstration at some point. Can you tell us about the architecture of the policy that is running in these demonstrations?
Thank you. Actually, in our case, so this basic idea is very, very little old one, but the basic idea is based on the world model sense of the world model. Oh, no, this is a very old idea. Okay, so so the idea is to currently everyone works on from pixel to or language to motion generation. In our case, it's an originally so that before actually so over 10 years ago. So we work on the similar world model. Actually, before the publishing the paper of the world model, but the idea is almost same. Because my background is cognitive robotics, which is making this new kind of finding from the neuroscience. And in this case, we input in the pixel and robot posture. And now it's going to be currently including the torque sensors and tactile sensors and predict the next functions. So now then many students work on this part and the neural networks for the transformer and diffusion models. So that's basically very close, but we think that predicted the next stage, so in the sense of the image or the cognitive state is very important at the sense of the power models to reduce in the training data. But yes, basically they're very similar things. So also now we're including the attentional models which part of which sense is important for the generating the motions. Or something now sometimes. This one is also the result which will be presented as humanoids after these conferences. And so we target the cooking. And so it requires to make the attention, the multimodal attention, not only the vision, maybe in this case increase the tactile senses. So there is the training phases. So actually see towards this motion, directly grabbing the robot arms to the wings and this kind of tools for the cookings. The robot self-organizing attentional mechanism. So in the beginning of the cooking, the main focus is vision. But during the cooking proceedings, attention will go to the tactile sense. More detailed architecture will be presented in this presentation as humans.
Okay, do we have other questions from the audience?
I missed to estimate in the time. So this is so preliminary result based on our association, so using fine-tuned. Actually, in this case, in the foundation model is not from ours, and we use Python. But Professor Inam at Tamagawa University and under their group, so the robot group, using their 5 hours data and based on our architectures from our associations and fine-tune this kind of motion. So the prongs and this line, the edges are automatically generating this motion. So I expect this activity continue connecting such open source criteria, not only the edges and with an foundation model, also some architectures, then we will show the more model extensions.
Maybe one last question would be, you showed us the open data set from AI grow-up.
Yeah.
Can you tell us about the size of the data set? And is it something we can download like on our computers today? Or
actually, it's not so. Actually, it's not really easy to see the final goal, but its final goal is 100,000 hours. So 10 times larger than the high level. Now you say so. And currently, so now we already collected 8,000 more hours exploited. And now, so firstly, we open for this kind of regular members, but some parts of the data will be open for soon. Yeah. Maybe at least mid of this year.
Okay. Okay, thank you very much. Let's thank the speaker again.
Thank you.
So now we will switch to our next speaker, Mr. Liao, who's online on Zoom. And so Huanwen Liao is a second year PhD student at UC Berkeley. He works at the Hybrid Robotics Laboratory. And he's also the lead developer of the Berkeley Humanoid project. So, if our speaker wants to share their screen, can you hear us? All right. Yeah. Just turning up your sound.
Hello everyone, can you see my screen?
Yes, thank you. Yeah, so the floor is yours.
あ、そう、こっちの音声聞こえてない。もしかして。
Oh wait. Okay. I cannot hear anything. It's nice. The audio doesn't synchronize. Okay. Hello everyone, I'm Xiaoyan. I'm the study PhD student working with CoRL, and today I'm talking about accessibility and capability in open source humanoid robotics. So, questions. What is the best open source robot? Here's a few hints. This type of robot, this type of robot has the largest deployment scale. It got deployed anywhere in the Earth, or even in the space. And it has the lowest barrier to entries. You can build one at home or use it anywhere. And it's at the highest impact on science and industry. The answer is desktop 3D printers. It has huge scale, it has huge impact, it's very open, and it is a robot. It has sensors, it has actuators, it has control systems, and the 3D printer delivers things according to the human command. And it's very success across current mechatronics projects. And this is also the reasons why I fall in love with open source. My first robot was an open source 3D printers, and later I also designed open source new 3D printers. And this is photos from like nearly 8 years ago. And the open design plus community support really enable fast learning and iterations. So why 3D printers succeed in open source? I think there's two main reasons. One is accessibility. A 3D printer is low cost, it's easy to build, it has huge community, and also is widely reliable. Another reason is capability. 3D printer is kind of novel, building a new novel paradigm, and is high precision enough, reliable enough, and is testable enough to be used in a lab or in a company. And the question becomes how to make that robots succeed in open source. We already saw some success stories like the MIT Cheetah series. They also enable some some new design parameter with new capability. There's also some very robots from the open source communities, from Stanford, from Tokyo University, from Open Dynamics Institute. They are all very success stories that emphasize accessibility. And our answers for humanoid is Berkeley humanoids. First, we built a Berkeley humanoid V1 for proof of concept, and then we emphasized accessibility with Berkeley humanoid light. And later, we pushed the robot to the limit with the Berkeley humanoid V2. Okay, now let's talk about Berkeley humanoid V1. We try to build everything from scratch, including the actuators. We built all types of actuators. They are all planetary type. We bought the motors, safety motors, out of box, and also the bearing. And then we designed different kind of gearbox, different kind of motor drivers, and use housing mounting interface to put them together, form or integrated to your actuators. And here shows the MEVIUS side. We're doing assembly for actuators. It's speed up, but it's still kind of wanting to do the mechanical parts assembly and also the soldering of the electric parts. And we need to repeat this process for 12 for mass production. Also, we design sensors and other components by ourselves, including the initial measurement units. We have some cell-phone grade MEU chip with our custom extended filters with the temperature controls to control the temperature of the chip. Remain the exact same level so that the bias doesn't change. We also have some foam to absorb impact. We also design a power manager to power the entire robotic systems, and by combining the actuators, the sensors, and other this kind of components, we are able to integrate it to your humanoid system. So we spent 10 months, we spent more than $20,000. The question is why all this spend? First reason is we believe we are able to build a higher performance robots. And the second is we want to transparent to the level there that we are able to access everything, including any line of code, any pieces of design. And also, I think we are able to lower the costs. And one important feature of this robot is built for learnings. We try to make it very easy to simulations and try to make it reliable. Also, experiment friendly. So we had a minimal composed policy, which didn't contain any perception informations, and also no histories, no teacher students. But it works pretty well. It can traverse uneven terrain or even do something like hiking, and it's very robust observations. It can also do some dynamic hopping behavior. Okay, now let's talk about the vertical light. The vertical light emphasizes accessibility. We try to find the parts that are variable across different countries and they are cost efficient. For example, these motors and the motor drivers are out of box. You can buy it in some online vendors and they are consistent apart. And for the structural parts, we try to do design custom actuators with cyclic gearbox. And we did lots of actuators evaluations, like measuring the efficiency, measuring the lifetimes, and the output power precisions. And also we did some evaluations on the arms. Oh, by the way, this project is led by another Berkeley PhD student, Yu Fengshi. He is also working on the Berkeley Human project. And we have full open source. We released all the code base and CAD designs. We had written documentations and get some guides. And everything is available at the Berkeley Human law. So the Berkeley Humanoid Lab is able to perform different kind of tasks with fair performance. It can do some manipulation, can do some tail operations, as well as locomotion. And it's like this picture shows people's around the world build their own Berkeley Humanoid lives. It's pretty amazing seeing our open source robot built in different places. Okay, now it comes to the Berkeley Humanoid V2. Here I only shows a preview of Berkeley Humanoid V2. We haven't released any information about V3 yet. So the Berkeley Humanoid V2 is aimed for the capability. We want to push the robot to this limit by having a high performance actuator and sensors. We got also custom everything, gearbox, controllers, emitters, and sensors. We try to do robust system integration, and we also come up with some new design tool for the gearbox. And all the hardware design, full firmware software stack will be open source. There will be document well, and we will have lots of meaningful results. But this robot is not designed for accessibility. So here's something to wait. I believe accessibility and capability is the key to success for open source humanoid project. And for Berkeley Humanoid, we have U1 for proof of concept, and the light version is for accessibility, and the V2 for capability. And our roadmap of open source humanoid is accessible entry points for everyone, and a path for high capability for advanced research. Okay, that's all. Thank you. I'm happy to take any question.
Yeah. Any question from audience? You can use the microphone around there. Yes, please.
Thank you so much.
Oh, maybe mic is not working. Yeah. Yes, if there is no mic, maybe the QM can hear that, so, or the wind.
Yeah. So, yeah. Speak, or we should wait a little. Go ahead.
Go ahead.
Ask
Yeah,
a
yeah.
shout. So, thank you so much for your presentation. Okay, that's what. So thank you for your presentation. I was wondering why was the main reason of open sourcing the lowest level of the actuator, and another one was related of what kind of material are you using for 3D printing? There's so many times ABS, VLA, and didn't you find any trouble with the heat dissipation when using those kind of 3D printer materials?
Okay, the first question is, why was the motivation of open sourcing the lowest level of actuators? I think we, inside the low level actuators, there's lots of details that also need to take care of, and also also need to be transparent. For example, the logic of protections and the logic of current controls. These play some very important parts in the synchronous transfers actually, but most of the existing commercial product doesn't have any kind of information. And also we are trying to build some new types of attributes, and we hope the open source project, open source of the loaded levels, can be similar to mini cheetahs, MIT mini cheetah, which proposed a new kind of design paradigm that enables the community to build upon. And the second question is, what kind of materials are you using for 3D printing? We're internally using PLA since it's the most common material used in 3D printing. And in this, we got some troubles when we pushed the robot to the limit, as there is heat dissipation problems and sunlight time problems. But like, as I said, this robot is built for accessibility, so we really try to make everything easy to build and easy to access, so the performance is fair. But we did lots of robustness tests. It's like you are able to do some normal task or like simple walking and manipulation, but for sure you are unable to do backflip or running.
Okay, thank you so much.
Thank you very much for your nice talk. I'm very impressed by the design. My question is mainly regarding the actuator for Berkeley V1. So first, I'm very happy to learn today that you went the way to designing your own actuator. I wanted to know how does this planetary gearbox plus pancakes compare to commercially available solution, price-wise and capacity-wise, like performance-wise?
I think price-wise is more expensive. The custom gearbox we use EDM for cutting the gears. It's you cannot compare it with like mass production of gears. And performance-wise, since we are customized everything, so I believe we are able to have better performance in under some task requirements. Yeah.
Great. Thanks.
Yes, thank you so much. So this is the last question. So thank you so much for the time. Okay, so the next speaker is the current year. Yes. So now the screen sharing should be working.
Okay, my name is Karen Liu. I am a professor at Stanford. Very happy to be here today because I usually not have the chance to be invited to give a talk about hardware. It's pretty far from what I usually do. But recently, I think Tanya mentioned earlier that at Stanford we built a toddler bot, and that's what I'm going to talk about today. So why do we build our own humanoid, and what do we learn from building our own humanoid? So I have to take you back to the beginning of 2024. It's literally the first day of 2024. My students came to me asking if it's possible to start seriously working at humanoid research. And we look around, we were looking at the options we have, the commercially available humanoids in the beginning of 2024, that was before Unitary G1. And we didn't like what we saw. Well, first of all, they're really expensive. And second, some of they're not even humanoids, they're just, human-like machine on wheels. One thing that caught our eyes is this little guy here. It's the OP3. We used to work with that robot. It's kind of things that we want to build, but the problem is that it doesn't really have the capability for manipulation because it doesn't have a lot of degrees of freedom on the upper body. But that gave us some idea. So my students said, well, why don't we don't like anything we saw. Why don't we just build our own robots? And it sounds crazy, but it's actually not that far out of an idea because our lab is known for building our own physics engine, for working on physics-based character animation. So now if we want to work on humanoids, it makes sense. We should just build our own robots. But before we, committed to that idea, the first question we asked ourselves is what hardware do we want for our robotics research? And the key word here is that research. Because we know there are a lot of robots, commercially available robots, that are really powerful, they have a lot of capabilities, because they promise to become a product someday. But if you really look at all the robots we have, humanoids specifically, we actually, those really expensive, powerful robots end up just being research platform for doing research anyways. So maybe we could just build something that's just good enough for us to do research. And yes, we still need, the platform to be reliable and capable so that we can conduct the research we want to. But we want a lot more than just that. We want something like super easy to repair because humanoids break all the time. It's, the fact that it's inherently unstable bipedal robots, we have to be prepared to fix that. And we want to have the ability to do that on our own. I actually took 3 illegal hands with me just this trip to Korea so that I could actually get them fixed and in time I could bring it back to California. Because the turnaround time of fixing your robots is just too much. And the second thing we want is a full stack ownership with no black boxes. Because we want to be able to innovate at the speed we like. And black boxes slow us down. It is maybe at the beginning, you feel like if you use someone else's existing work, it will save your time. But maybe that's just for implementation. For us, if you want to do research, you want to innovate, black boxes in the long run will slow you down. That's what we believe. So we want to have total system level understanding of the entire stack. And then we need this platform to be able to do large-scale data collection. Nowadays, when I look at robots, I don't see it just a platform for performing tasks. It has a dual purpose. The outer purpose of that platform is to collect data. And we want to be able to build that dual robotic system from scratch. And then this robot also has to be simulatable because we want to be able to support RL, sim-to-real RL, and building this digital twin at the same time as you build this hardware is, in our opinion, the only way to go to make sure that digital twin is very, very precise and ready to be simulated. And finally, this is a bonus point. If at the beginning we just want to build something for ourselves to do research, but if we can reproduce that very quickly, that means everybody can do it. And that's why open source, open project becomes one of the things we want to do as well. Okay, so if you look at this list, maybe the first item is something that you can buy, but everything else we want is not something commercially available to us. At this point, it was very clear to us that we need to build our own robot. And we can't even sacrifice maybe the capability a little bit or reliability a little bit because we are not pretending that this is going to be useful product in the real world anyways, and we're not going to sell this for money. So we just want something that we can do research with. Okay? So why is building our own humanoid even possible now? That's a question I ask my students right away. Definitely there are a few technological breakthroughs that you can point to, like QED motors, batteries, high-density batteries. But there's also something that's less obvious to me, at least, which is the new hardware design paradigm. A lot of those technologies that I would say converging technology that create this very, very welcoming environment for hobbyists to prototype, to tinker, to design something from scratch. And that's not something they had before. So for example, 3D printing technologies, free online CAD software, customizable PCBs, and also just onboard computes per mass unit. The improvements of all these technologies, supporting technology, just converge into a new environment, new hardware design paradigm that enables everybody. So this is almost unthinkable like 10 years ago, right? Because probably just a few places on Earth 10 years ago can pull off a humanoid platform. But now you start to see that everyone can build their own robot. And to me, this is really the reason that we see this new industry of a humanoid that jump-started. And of course, AI helps a little bit too. All right, so with that, I'd like to introduce Stanford ToddlerBot. ToddlerBot is a full-size robot. This is a miniature robot that has a 30 degrees of freedom. It has a lot of upper body degrees of freedom allow us to do research on full body manipulation. We also have sensors, fisheye cameras, allows the ToddlerBot to see. It has microphone, speakers, so you can communicate with Toddler. We call it Toddy, as you can see the name on the chest. It's pretty small. Actually, we have the Toddy right here. So also you can, stay there. If we need it later, we'll bring it out on stage. So the whole thing is 3D printed, and the motors are commercially available. The whole thing's about $6,000, but the price probably could be cheaper if we can have some deal with our motor providers, our motor vendors, because 95% of the price that in this $6,000 is for motors. We have a lot of degrees of freedom, so the number can add up. So just some video to show the first version of Toddy. Toddy is able to do manipulation, bimatic manipulation by training a diffusion policy. So we can use our system to collect a lot of data. And Toddy can also do reinforcement learning for walking. Toddy is actually pretty strong for exercise, so we can also do pull-up, push-ups, all these interesting upper body motion. And here is an example to show the combination of diffusion policy and RL locomotion. And we also want to demonstrate that this could be reproduced easily. So we built a Level 1. We printed Toddy, a little sister, so that they can play together and clean our Stanford Robotics Center every day. All right. So here is the next version of Toddy. This is more, I think we redesigned the waist to make it more sturdy. So they can, Toddy also can crawl and walk at the same transition between those two modes of locomotion. Here's probably the most dynamic motion that Toddy has ever done. Successful rate is not as high as we hope, but it's beginning. Here we have Toddies doing all different kinds of locomotion with rough terrains. It's pretty rough for Toddy. It has to climb up and down the stairs. And so what we did is we designed multiple RL policies, and then we have a hierarchical higher level policy to route between these policies. Okay, so a lot of, I also get this question a lot. Why do we design something so small? Well, there are many reasons. The first reason is I want something very safe. Safe enough for one person to operate. Because when we're doing research, oftentimes you don't have a team of support to help you do research. You're alone with that robot in the lab at night. I don't want anything to happen to my student. So this is a video that my student sent it to me, Yanjie, and he's been working with G1 for a while, so he was just, I taught audio here because when you hear the audio, that's even more scary. So this is the kind of thing I will never want to happen again in my lab. And I want something that, when only one student is operating, it's guaranteed to be safe. And being small is one of the guarantees that we can provide. Another reason that we have a really small robot is because it's actually a consequence of using 3D printing materials. 3D printing is great. It's good for reproducibility. It's good for repairability. But it also imposes a constraint on the size of the robot that we can build. First of all, it takes forever to print large parts, right? But even worse consequence is that materials deflect too much with large size. Here is a very simple equation. You can see that if your material is not stiff, then your size is also constrained in order to bring down the deflection. So we did a little bit, so we kind of have to build a small, we weighing our pros and cons, we decided we still want to go with 3D printing materials, but we just want to keep it small. But even if it is small, doesn't mean it has to be weak, right? We can build a tiny but mighty little robot. So one thing that we wanted to do is to make sure that Toddy, or Toddlerbot, has the same relative strength as as an adult human. And the way we compute the humanoid power factor is to basically take its maximum torque capacity, normalized by its height and weight. And to us, this is pretty reasonable because you can think about Toddy pretty much has the same strength as the ground humans in terms of carrying its own weight against gravity and also travel its body length. However, there is something that prevents us from shrinking Toddlerbot even smaller because of the dead weight, right? So no matter what you do, there is a certain amount of dead weight that robot has to carry. For here, the compute, the power supply, cables, communication boards, all these things add up to about 650 grams, and that is something you cannot cut. And if you make your robot smaller than, we did a little calculation, if the robot is smaller than 50 centimeters, then the humanoid power factor will be sacrificed too much to the point that it doesn't make sense anymore. So there is a lower bound for the size that we can go down. Okay? Another really important factor for us to do when we design the robot is the machine learning capabilities. We want to be able to support all different paradigms of machine learning or robot learning. We want to support imitation learning, sim-to-real RL. We also want to support real-world RL learning training. So for supporting imitation learning, we make sure that the teleoperation is possible with Toddy. And we build an upper body of Toddy. It's an upper body replica of Toddy. In addition to that, the operators can also use the gaming control to see what Toddy can see, and you can use the controller to control the direction and the location that Toddy is traveling in space and where the neck is turning. So this requires two people together to puppeteer Toddy, but it can be done very quickly. So within 1 minute, you can get we did a little bit of calculation about 10 samples for manipulation. Another thing to make sure tile operation is possible is that we need to have a very robust balance controller. So no matter what you do with their upper body, tile is not going to fall on the ground, because this kind of a balance control is not something that operator can provide to tile. It has to be autonomous. We also want to support sim-to-real RL, and this boils down to how do you build a very, very accurate digital twin, the URDF file, right? So one thing, we know that URDF file contains geometry information, inertia information, as well as motor parameters. So we need to get them all right. Geometry information is easy to just get from CAD, but inertial information, if you just weight those 3D printing parts after you're done printing, is actually not that accurate. So we end up using the 3D printing path to calculate the mass, especially the mass distribution. And because you can see that there's a lot of like the interior part and the outer parts of the 3D printing, the density is very different. So the only one truth here is you actually just follow the path, because every small line segment of that path is actually solid. And then with that, if you integrate over the path, you can get much better inertial calculation of the 3D printed parts. We also do a lot of work with the actuator characterization. If you use Mujoko, you know that there are 3 parameters that offer, but turn out that there are way more parameters you actually have to identify. One thing we found very important to identify is the torque, the maximum torque limits, the relation between maximum torque limits and the velocity of the motor. In general, this maximum torque is constant, and it starts tapering down a little bit when the velocity is really high. But we found out that this behavior is only true when you're accelerating. If you're braking, you'll have a lot more capacity. The maximum torque is a lot higher, and that allows you to push the robot to its capacity more. And finally, we support real-world RL. I will just skip this part and show you the results. So this is also a CoRL paper this year. We try to train Toddy to walk, and the way we do that is we hook Toddy to another robot, an arm robot, a manipulator robot, to provide curriculum during training. So let me just show the video while I'm talking. And this treadmill also is part of the curriculum. So at the beginning, the arm's trying to give it more support, and in the course of training, this support is reducing based on the reward Toddy is getting directly from the real world. And after 60 minutes or so, Toddy is able to walk. With this kind of a real world setting, we can provide curriculum, but in addition to that, it actually gives us a way to protect the robots at the beginning of training, and also figure out a way to reset the robot. Like every time you terminate an episode, the only way to reset a robot in the real world, the only thing you need to do is lift the arm and put it back down. And here, let me just show you one last video. We're trying to train Toddy how to swing from scratch. And you can see the time. And the whole point of doing this is that we want to be able to do this without any human intervention. You just leave the robots there for about 15, 16 minutes and come back. The robot learns a new skill. You can let it run, but this is my last video, so I'm happy to take questions.
Any question? Yeah, you did the mic. Yes, fine. Yeah, we can take the question. So please now.
Hi, Professor. It was a very great presentation. So what I wanted to ask was mainly with regards to how you mentioned that Toddy can be a good research platform to study, let's say, different RL policies and how it can be a proxy. So similar to how we see simulators as a good proxy to study, or to train RL policies, and then the simulators to really have this gap. I am kind of wondering how talking to let's say adult robot gap would be there. Whether we can see a policy that is, let's say if we compare two policies on Toddy and say policy A is better than policy B, can we say that it will have a similar comparison in adult robot?
Yeah, this is a embodiment gap, right? You know, this is probably one extreme case of embodiment gap. So I cannot really tell you that if Toddy suffers less of embodiment gap from robot to robot, because that's not something that we actually, explicitly designed to avoid embodiment gap. It's just one, embodiment that we commit to. However, because we designed the whole thing, we can modularize the way we want, right? So I think a lot of things, if you have this total control from design all the way to control policy, you can do a lot of things to overcome that embodiment gap without being slowed down or impeded by the black boxes in the middle.
Yeah, thank you.
The joints of Toddy are different from other humanoid. It uses like servo motor, right? Do you think it will limit the performance of the Toddy?
Yeah, so I think that many things that might limit it, but that particular case, actually, Houghton, do you have any thoughts on that?
Yeah, so I think the cartwheel task demonstrates hardware capability of the servo motors. And actually for the cartwheel task, we haven't pushed the motors to its limit. It's still the symmetrical gap is limiting the success rate. So I do feel like the servo actuators have more potential to explore.
Thank you.
Question? Thank you for your great lecture, and I have some question about how does it take to make one model?
How much?
Time to take.
How much time to take?
Make one model.
Well, for Houghton, probably 3 days. Would you say that? Or better now?
Better now, maybe
Better now.
1 to 2 days. If
1
you
to
are
2
the
days.
first time, it might take 3 to 5 days.
And what was the research time? It may be 2 days for final, or you may have some kind of trial and error. So total time of developing first prototype.
Total times of development versus what?
For the first time, total time of making the first prototype.
Oh, like just develop this whole thing. It took us a year. Would you say that?
Yeah.
About a year for the development, because we went through many iterations.
And actually, I have a question. So, other humanoids use some motion capture data, and they can return it to the robot. And I think the total robot has kind of different ratio with the human, so it cannot directly use the motion capture data. Right? So if you're
We actually tried. So there is also the problem of embodiment, and then even the software on the animation side of it we call retargeting. So we could do that with the toggle bot as well, and we did that with some motion for that. But we also found that it's very easy to just create keyframe animation for toggle bot, and you just put a toggle bot into different poses, interpolate it, and that's a lot faster than going through human motion route.
Demonstration use some of the first video, pushing the character, manipulation was the key.
Yeah, no, the manipulation is actually toggle operation. So we use the toggle operation because we need to collect both the visual, the egocentric observation paired with the action.
Thank you.
Thank the speaker again. Alright, so that was the poster and demo session. So please enjoy coffee. Poster presentations are right in front of the room. We have 6 posters, and the demonstration booth is booth number 2 over there. For posters inside the room, there are magnets here. We are going to put the posters on the doors. You heard correctly, those are the official instructions. Please come to me for your magnets.
Actually, there is only the 3 or 4 posters can be inside, but other posters can be outside. We can have a paint, so not on the poster board, but we can paste the poster on the wall. I think it's the workshop organizer's decision, sorry.
Outside on the walls. Because then you also get some more exposure. People are going to walk in here, but they will be outside. Just check out people are just trying to stay. Yes, actually there are some places where so nice. Also go outside to find people who come in here.
Nice, thank you.
You have a camera?
And it is a second European student now.
No, I mean,
it's mixed, but
Was it okay? Yes, just put it outside. I think it's perfect. It works very nice outside.
But I mean, you have like a workshop paper and a simulated paper. Doing the right. Is it the public?
Public paper. I don't think you have a problem.
Viens, on est assis là, si tu veux. Attends.
バッテリーが
バッテリーがね。
いや、ないとか、あそこもないんですよ。でここは一応配信用にやってるんですよ。ここしかない。
So can you tell us about the effort that this company has made in open source robots? So Juan, the floor is yours. Thank you very much.
Thank you, Stefan. Today I'm an engineer at Plan Robotics and Northern Office. The Poland is a robotics company that started in 2016. And earlier this year we have been acquired by Hugging Face, which is an AI company. And they believe that robotics will be the next big thing for AI, so they are ramping up. So today I want to present to you a few projects that we've been doing at Poland and Hugging Face. We do most of what we do is open source and open hardware. And then I will focus on a specific project which is the Mini, and that's mainly because that's my project. Here we go. First is Richie 2. This is our kind of flagship product at Poland Robotics. So it's a product that we sell, but it doesn't mean that it can't be open source and open hardware. It's a humanoid torso without legs, so it's made of two arms and a head and mobile legs. It has 7 degrees of freedom per arm. One specific thing that is a little specific about this robot is that it uses parallel actuators everywhere. So for the shoulders and the elbows, we made custom parallel actuators that we call Orbital 2D. So you have 2 degrees of freedom in the same point in space. And for the wrist and neck joints, we have the Orbital 3D, which gives you your 3 degrees of freedom in space. So you would have your pitch as well on the same place. So we use it for the wrist of the robot and also for the neck of the robot. And something that we spent a lot of time working on was making a nice and easy to use the teleoperation app. So you put on your headset, you see through the robot's eyes in the stereo, so you can adjust its depth. And you control the VR with the VR controls. It makes it the animation is not very smooth. Sorry. Makes it very intuitive and easy to control the robot. It's pretty hard to get it right because, as you may know, in VR you can get sick pretty fast if there is too much latency. If you don't feel like your brain cannot like it, and it's especially harder when you make a robot, which is a physical thing in the real world. So we worked a lot on reducing the video latency, the movement latency, and having as many FPS as possible, and to have a field of view that pretty much matches make you feel comfortable. We also provide for this robot really high level and easy to use Python SDK. So it's easy to it will come. So it's easy to build the behaviors for that robot. And it's all based on a ROS2 stack. So we just keep on going. Since we are now part of the Hugging Face also, our robot is really integrated in the robot library, which I will talk a little bit more about just after. And so with our teleoperation app, we can collect training data and train some policies. Maybe you can start sharing and try to So in this example, we show we use our teleoperation to collect data and then train the policy using ACT. I will just move forward because so the lower library is a library Hugging Face when they started doing robotics maybe 1.5 or 2 years ago. And its goal is to make AI for robotics more accessible with end-to-end learning. And I think there are two sides of the way this library is important and interesting, is that it re-implements state-of-the-art learning algorithms in a clean way, in the standardized way. So algorithms like ACT, diffusion policy, GDMPC. There is also a new VLA made by the Hugging Face team, which is a small VLA, which is a minimal implementation of a VLA. And it can be trained on data that is freely available on the Hugging Face. And the second aspect of this, in my opinion, is the dataset format, which is starting to get pretty widely used. Right now we have.
Sorry.
Right now we have about 16,000 datasets on the hub, so it can be a very small datasets of maybe 50 examples, but also contains very large dataset. And it's also starting to get very popular with more than 17,000 stars on GitHub. And also I think that one of the reasons why this has become so popular is because of it came along with the SO100 arm, which is a very cheap robotic arm that you can build really easily. So you can the leader and follower arm, you would control the follower arm with the leader arm to collect some data, and then train some policies. Many of these arms have been built by hobbyists in research labs, pretty much everywhere. There was a huge worldwide hackathon a few months back, so it's a very popular thing. Next is our newest robot is Richie. So this is a desktop robot that is really meant to be a human-robot interaction platform for to experiment. It has a microphone, a speaker, a camera, and it can move around its head with the 6DoF Sierra platform. So you can do full rotation and translation. We also added a body so that we can move its whole body. It has an antenna, so basically it's pretty cute. That's why people like it. We provide also a simulation environment and easy to use Python SDK. Our goal is that it's fully transparent. You can develop your behavior in simulation and just plug your robot and run the code as is. By the way, you can go see Richie in action at the demo time I will show you. And another project is the MEVIUS, so it's 4-figure 10, because why not? And it has 2 different per figure. It's mostly 3D printed, it's not very expensive, and it's also made of a parallel actuator. We like parallel actuators at point. I mean, it's a parallel mechanism, so you have 2 motors that control the finger. If the motors move along, they will do the flexion. If they move the opposite way, they will do this movement, the adduction, I think it's called. And you can basically do anything in between. Another gripper that we developed, which is based on the Richie Tooth gripper. So Richie Tooth gripper is much more expensive because it's made of built aluminum. It uses much better motor, it's more robust. But with this version, which is scaled down a little bit, and it uses a really cheap motor, you can still do a lot of things, and there have been many reproductions of this design to be put on SO100 arm, other robotics arm. Okay, now I want to focus a little bit more on this project, which is the OpenMP. So you may have recognized it. It looks a lot like the Disney robots, the EDX robots. So what happened is that when I saw them, I fell in love basically. I really wanted one. So I decided, okay, let's make one. And it was also at the same time that I wanted to start learning some reinforcement learning. So yeah, let's do reinforcement learning for robotics. It would be really easy. so I wanted to make a low cost, in the end, the goal is to make a low cost open automation platform. Really low cost. And the main challenge was that because one of the goals was to reduce the price as much as possible, the motors were really cheap and so hard to model, hard to predict exactly how they would behave. So this is actually the second version. I plan on showing the first few slides about the first version, but I don't really have time. This is fully open source. You can find everything on the GitHub repo. So from CAD software, from the CAD to the software to the electronics, which is mainly the shelf electronics, and everything in the training code and any data. There are some good instructions, and yeah, total BOM cost of the robot is about $400, which is really, really cheap, and it's actually a little bit less if you can find some suppliers. It features the bulk of the price is these motors, which are the same that are used in the SO100 and 100 pound. They are really good for that price, meaning that they are between $10 and $50. So it's pretty much unbeatable. They are pretty turkey, but yeah, really good for that price. It has a standard AMU Raspberry Pi Zero, which is not a lot of compute, but it's actually plenty to do some inference of locomotion policies. I can run my locomotion policy at more than 1,000 Hz if I want on this small computer. On this version, I added foot switches. The idea was that it could be interesting information for the policy to know when the foot is touching the ground. Actually, I think we don't really need it, but it can help. Also added some expression features. So we have the eyes, which can blink, the speaker, the camera, and flashlight are the antennas that can bring some expression, and it's all powered by 660 track. So for the reinforcement learning, it's pretty simple. I think the bulk of the behavior is learned through the imitation reward. So also very inspired by what these neighbors have been doing. They published a paper explaining their method. And the idea of the imitation reward is that we generate some, like you can see in the bottom left, some trajectories with the whole pattern generator. Here it's a plateau. And we would sample trajectories based on the velocity task. And then during the training, one of the rewards would be to match this trajectory with the joints, depending on the command that was given. And there's also a lot of representation, very classic stuff. The most important thing was this idea, was really making that we simulate the motors accurately. And it was hard with these motors, but it was most of the work also understand how these motors work, because it's closed source. We don't have access to the firmware. There is not a lot of documentation, so we did some reverse engineering to really understand how they work. And in the end, it works pretty well, but I think by digging a little more, maybe having some custom firmware, it could work better. One other thing also that was needed was to have pretty conservative policies. Highly dynamic movements don't work very well with this robot, because I think we are at the limits of what the actuators can provide. Also, classically, a lot of noise, the randomization, the delays, and having random pushes during the training. What we want to do to improve in the future is train the policies with the work AP. Right now, the motors are pretty stiff. So maybe to be better to produce some smoother behavior, to have smoother motors. Also switch to the 12-volt version of the motors because they are the same price, same form factor, and a little bit more powerful and fast. Also, behavior, something that we noticed in this robot that well, it's in every robot that uses serial servo motors, you lose some voltage in the, so you would have the motors at the end of the chain would have less voltage than the motors at the beginning of the chain, which is something that we could model. Also, when there is dynamic movement, the voltage can drop, so it's something that could be modeled to disintegrate. Something that is also we would love to do is to be able to run episodic motions, so to show some emotions, some animations basically. This also has to be trained through the reinforcement learning pipeline, because it's a very robot, it always has to maintain its balance and not showing emotion. And yeah, it's been a pretty popular project. We have more than 2,000 stars, 2,000 people on the Discord server. I've seen about 50, maybe a little more, working reproductions of people all around the world. People are making this robot, and they're making it work using the methods that we provide. We have more than 100 people that are actually actively building the robot right now, and the community is pretty active in helping each other. Some people are really keen on helping develop the project. They have good ideas. They are really interested in beta testing, writing documentation, making mods to make them look better. You can see some of the mods that the community has made. And having a community like that really helps improve the design over time. Because yeah, I can't always think of everything. You do your design. It's okay, it's cool. I can make it myself, but then you put it in the hands of people, and they say, "Oh, this is not. We could improve this. We could improve this." I think the community aspect of this project is really help making it better over time. So yeah,
Any question from the audience? If you have a question, then come to the mic, please. Yeah, ask a question. Okay. Yeah, should be the place of the mic.
Yeah, it's working.
It is.
Yeah, go ahead. That's the right
one. Hey, thanks for the talk. I was actually curious about the comment on closed source servos, and wondering if you or anybody in the industry is working on open source firmware for existing servos, like reflashing those, or just open source servos in general, because that seems to be like one of those critical areas in all robotics, and I don't know if anyone's.
Yeah, that's really something that we want to do. We started working a little bit on that at Poland. About writing your own software for proprietary server, they didn't seem to like it. Because you could make it so that the motors basically burn or hurt people. So they don't like the company that we have been in contact with don't really want us to build a custom firmware, which an open source firmware, which to me is a missed opportunity for them, because it would really improve the usability of their server, or at least they could open their firmware or document it a little more. But I agree with you. It's probably one of the pain points in using cheap off the shelf servers.
Thanks.
Okay.
Thank you for your talk, and I'm very interested in open hardware and open source. And I'm working
What is, can you repeat the question?
What is your business plan to get money to develop such an open hardware? So many open source community is difficulty having a difficulty to get money to develop.
Yeah, we are actually in a pretty privileged state because we have been acquired by a company that has money and is really interested in pushing the open source. It's in the core values of the company to do things that are open source. And the business plan, for example, for the Richie 2 robot is that you could build it yourself if you wanted, but it will be pretty hard because there are a lot of custom parts, custom things that are made in aluminum. So making it yourself without any scaling in the production would maybe not be very interesting money-wise. So it can be an option to buy it from us because we can do some economy at scale. But we still will provide everything if you want to customize the robot, to change things to the firmware. So yeah, that's it.
Okay, thank you.
Last question.
Thank you for your work. My name is Keith, and I would like to ask you one point about when developing OpenTech Mini and open sourcing. I mean, as we already know this kind of robot was first, let's say, developed by Disney, and then, okay, let's open source. So many of us who are working in open hardware, the main, let's say, reason because many of them, they don't want to make it open is maybe the copyright infringement. What was your, let's say, your points to be careful when open sourcing this robot?
I think it's a robot that kind of looks like well, you can recognize it, but in the end it's very different from what they build themselves. Also, I think the main point is that I'm not trying to make money in any way with this project. I'm just giving it giving it away to whatever you want with it. I didn't get a cease and desist letter from Disney yet. Crossing my fingers. But I think that if I decide to mass produce this and sell it as a toy, I don't think they will like it.
Thank you so much.
Okay, thank you again. The next speaker is Boyon Chen from Duke University, Duke Illinois. So, hi, can you hear me? Can you hear me?
Stop sharing.
Please stop sharing.
So today I would like to share with you some of
open source robot came out from our lab to do. What we really try to push here is try to look at the first principle that we're looking at here is try to try our best to model user human species and specifically on the mechanical structure and see how the mechanical structure will bring benefits to the control principles. So this is sort of like a CAD model of robots. The robot doesn't have arms yet back then, so there are 2 legs, and the diameter is typically around about 1 meter. And you can see that the some designs here at the left are parallel linkage, and it turns out that we actually don't quite have this design because of the simulation difficulties. But you know, what we actually try to do is because of the mechanical structure design, we're able to have the motor placement such that we can achieve static standing gates. So in this case, the robot is able to stand passively without activating the motors. And in fact, this is quite different than the humanoid robot I've seen quite a lot in previous examples where the robots may need sort of bend their knees and still actively activate the motors. In this case, it saves a lot of energy. So this is sort of what it looks like. We also train reinforcement agents in simulation, and then deploy them as zero shot after the system tuning. Here you can see that the robot can develop quite successfully in this setting. But this is sort of the baseline reinforcement training. The second idea we look at is, humans will be modeled. We really always turn our motors on. In fact, sometimes we turn some muscles on, sometimes we sort of leverage the passive dynamics and swing the lab forward. So we have this sort of simple idea that how do we inject this kind of passive dynamics mechanism into an end-to-end reinforcement setup? So in this case, the formulation is quite simple. Just from the traditional PD control, what we can do is add a modulating factor alpha here that the policy will not only output the change of actions on the motor commits, but also a modulating factor here that you can selectively turn on or off certain motors while you're walking. So you can sort of modulate each of the individual motors first while you're actively using reinforcement policy. So here on top is the basic baseline our reinforcement policy. At the bottom, this is the passive dynamics. So if you actually pay attention to the upper body, you will see the baseline policy shakes the upper body kind of back and forth a lot. Well, the bottom line sort of only shakes because of the leg movement, but kind of blocked in a more energy efficient manner. So in fact, when we measure the cost of transport in the real world, we can reduce about 31% of the cost of transport in the real world by using passive conversion. So, but this is really the first version of the humanoid. Right after we released this archive, we actually completely open sourced everything, including high-level code to do the reinforcement control, low-level code, motor control, sim-to-real, system identification, hardware design, 3D printing parts, scenes, machining parts, and even a fully online website with example menus. And the goal is really that we realized that there was a very limited number of humanoid robots being open source. But there is sort of a trend that the community is really interested to explore how with the modern robot learning algorithms with the more affordable hardware design. And we're excited to share that the humanoid V2 will come also this year. And this time we're adding a lot of changes to completely redesign the robots, and there are 50 plus unique machining parts. And with similar heights as the first one, but now this time we have ARM and manipulators. So we're going to have some very good demos released there, so please stay tuned on that. And our plan is to do the same, and we'll completely open source this version of design, and we'll learn a lot of lessons from our previous ones, like parallel linkage, the motor replacement, or the mass distribution, all give us a lot of trouble in the first version, so we hope to resolve all of those in the second version. But the second principle I want to really talk about today is, if we look at the first one, it's almost we're trying to copy particular type of species. In this case, it will be a human design. But the second way to learn this would be how do we automatically, just like nature generating all having diverse species So in fact, one of the things that I observed is that I teach this class of Robot Studio I do is essentially within one semester, 90% of the class or any students will form typically a single person or at most a pair of students who would work together to do a Lego robot. So the only principle or rule in this class is that no wheels are allowed, so you have to do the Lego robots. It's more challenging, it's more fun, and you can put a lot of your personality and creativity into it. So here you can see that students indeed come up with lots of different designs, and through the past few quarters that I've taught, eventually at the end of every semester we have this walking and dancing competition in front of the chapel. This sort of photo that we took in the first version. And what's really cool is that every team was able to build a robot from scratch by sketching your ideas on paper, all the way to using reinforcement or aperture algorithm to generate gates to control the robots. So you can see that even with a group of N number of students, and most of them are basically the first time ever for the computer robots, that the robots are really diverse. And this really gives a lot of opportunity to explore potential, optimal morphologies that we're looking at, different creativity, and even making our personality into robot design. So my training about robot design really started about 12 years ago. This is from a cover of economics where people talk about the third industrial revolution. And the dream back then is that a human would be able to sit behind a computer, type into what you want, and then the rest of the process will be fully automated. And then you generate airplanes, tools that you want, or transportation tools, all kinds of things. Obviously, we're super far from it, but you would want to get closer to it with computers and robots. So to that, we introduced text robots, and this was published in April this year. The idea is to have a human to input a single text command. For example, I want to build a robot that looks like a shoe. Well, you can specify the needs. For example, you want a robot to track a user at the velocity, or you want a robot to be able to save energy, for example. And then the rest of the whole process will be automated completely by AI. So specifically, the way that this works is by leveraging the generative power from the first sort of wave of the text creator model. So if you think about all of these sort of really amazing AI tools we have nowadays, you have lots of tools that can generate going from text to meshes. However, one of the bigger challenges on the meshes is that you will generate a static mesh, you look at it, you may be able to load it into assets, but you can't really animate it, you can't really know how to route it to a physical machine, and not mentioning being able to know whether it is a good design or a physical one. And then on the other hand, it gives you like how the signature design of the robot, most of the robots, how they are reported, or like our humanoid robots, it takes sometimes a couple of weeks, months, all the way to a couple of years to run the design. So our idea is to go through the first step is to use the text 3D model to generate thousands of different variations of robot meshes bodies, and we're going to segment them based on different hypotheses. For example, where do we place the motor, where do we place the controller of the motor, where do we place the battery. So we kind of simulate all of these variations all together into the robot. And then it's going to couple with reinforcement to train every single one of these robots, their locomotion policy, and then you have to design criteria based on their velocity tracking or your careful energy saving. At the same time, all of these species will go through a evolutionary algorithm that is going to co-evolve its body and swap part of its body with others. Maybe out of their point is better than mine, so I'm going to take that part in my process. And after all those generations, a couple of hours, we can end up with this process where you send the file into the picture, it extracts all the motor boxes for printing. So what you do is snap them in. So you've got the whole assembly process take about 10 minutes, and it doesn't require any screws in there. You can just place them. And because of the reinforcement policy has already been trained for this robot, you would just directly deploy them in the real world. One thing that we've learned on this is generative AI really gives you a very good starting point. So back then, the state-of-the-art robot and policy co-design was robot grammar, question here is really the policy performance in the first iteration. So this means that there is no learning, there is no evolution process happening, which is directly taken random initialization from text robot and program. And what we do is directly train the initial version of the policy and measure the reinforcement reward. So here you can see that most of the robot stays with very low reward. And part of the reason is that when you randomly predict shapes together, it lots of them are not simply not valid design. For example, you're going to have robots that have self-collision, you have robots that doesn't really place the joints in the correct orientation, and they simply would line on the ground and doesn't really walk. In contrast, text robot, because it learns to generate various kind of shape or animal species based on a single word, and in fact, if you send one single word, say, I want to generate a dog robot, the text is pretty measured, it's going to generate lots of different variations. And if you directly take this robot, right, before we even involve the shape, you're going to see very high reward function. So this is in fact my first time to see that when you train sort of evolution algorithm together with reinforcement policy, you're going to end up something that already starts very high, and the rest is sort of like a fine-tuning of the design, and in much faster iterations, fewer iterations, you're going to end up with a very good design. Even the policy and robot end up with already very good design. So here you can see sort of at the beginning, right, this is really the robot before they learn anything, they can already learn raw pretty well, and later on when you go through various generations, we're going to see robots getting better and better and match the user preference. And one of the cool parts is that it's also scalable, right? So if you only input one type of morphology, for example, I just want a dog robot or a dog robot or a frog robot, all of these will still be to learn, but not be to capture the highest reward. But if you input, in this case, 10, 20, 30 different words, just let the human be creative on creating word text, you will end up with something like the purple word, in this case, simply increasing the number of words you have in there, you will end up with higher performance on certain robots. So here, this is what it looks like when the robots are directly deployed in the real world. And you can see that it looks like a bug or a frog, it did end up with different shaped body shapes, but the food node also gives you a slightly different variation. And in this case, you can see the energy efficient version essentially gives you some robots that actually with a shorter body, where the ones that are optimized for velocity will give you a taller body, in this case, a longer body with longer legs, so it actually walks quite fast. And if you look at attention, right, so what matters are the details. If you look at closely, the joints placement and orientation all matters for them to be able to walk, and track different kind of velocity commands. You have left, right, and forward, it's able to do that only because you have the correct joint placement. And if you throw these robots into various different terrain structures, you're walking on more of these bridges, also the robot typically would end up with something like this in the middle, where if you ask you to walk on some really rough terrain, you end up with some sort of robot with a round shape. And typically that's because the robot will get stuck if it has this kind of a rigid design of the food shape. So this is quite interesting that the algorithm itself is able to discover optimal morphology like this one, even focusing on kind of little part of the robot. So that's the second principle. And the last principle that is something that we feel very excited about. So we're going to release the paper in the next few weeks, but very excited to share here with you guys, is to go beyond talking species, right? If you look at the first one, whether we're learning from a generative prior or we're learning to imitate a particular species, well, we typically end up with kind of going to something like a dog or human, and end up with robots like Boston Dynamics, quadrupeds, or like humanoid robots. If you have human head works, you can end up with robots like this ones. But we wonder, what are the other guiding principles we can follow on these kind of robots? And to me, what that really means is that to look at sort of one more deeper level of the shared fundamental principle along perhaps almost all the nature living existing things. And what's that? So if you look at all the nature living existing things, including the plants, snowflakes, flowers, trees, animals, humans, we all follow, almost one shared principle, which is symmetry. We barely see anything that does not follow the principle of symmetry in the nature of these things. So in this case, we wonder what will happen if you just take that principle and push that to the extreme and bake that into the robot design. What kind of robots would end up with, and what that property really will bring us to. So that is Argus. So this is taking the first name from the Greek mythology with all eyes on its body. What you see here is a robot with 20 independent legs that kind of actually stop in as a linear actuator, and then 20 cameras around at the tip of the fluid. And because it has all this 360 view, it's very robust, and it can do lots of movements, right? So what I'm showing here is the robot is able to follow arbitrary trajectory, that you command robots to go through. You can have robots that is able to walk even though 3 legs are completely being disabled. You can still walk forward. And if one of the camera is damaged, all other cameras can still see. So there's really no path for this robot. Any direction is the right direction. And you would get active control with self-visualization, right? So here we're students pushing it, and the robot is able to stay in place. Or you have robots that can actually carry 10 pounds of payload, being able to walk forward, even if it's never been trained to do this. And all of these you see are zero-shot transfer. I really love this robot because this is the first robot ever that takes the shortest time for us to do things real. Everything that it does is at the end of the day, we're able to get one leg tuning for serial transfer, and the rest is full. And we never need to worry about that never all tasks that have shown. The other case is the robot is able to traverse through, obstacle, history obstacles. It is able to block, an outward domain, even though the only thing we've trained it is walking on a flat terrain. It's able to go through the grasslands. So I'm going to speed up the video a little bit so you can see it actually go through. This is on the campus. Lots of different locations, even though it was just rain, it's able to go through. And next to the water, go to the concrete floor, walk directly on, in the woods. And this is where we're bringing the robot into a conservation area where you have the sandy area that the robot has no problem to walk through. You can see the robots can climb into a parallel walls that enter the gravity. And each one of these lab actually generated very small torque. Generated almost 300 Newton peak torque and 100 per second peak velocity because of the design of converting the rotary motions into linear actuator. And because it has cameras on the body, it is able to track, and follow particular objects. And even though, we didn't really know the initial pose of the robot, you can randomly place the robot in any arbitrary pose and drop an object. Is able to follow that with, various kinds of trajectories. So I'm going to speed up this a little bit so you can see that it's able to follow with its onboard camera. And in these cases, the robot is even able to push an object to a perfect location using its onboard camera. So in this case, it has to manage to manipulate an object at the same time being able to have a stable motion given itself. And what's cool about this robot is also it's sort of shape working, right? So if you look at here there are 4 different types of tasks. The robot exhibits sort of different average shapes that actually try to maintain, and kind of the preferred positions of each of the motors that stay roughly around the same place for specific task usage. So you can see that it exhibits different kinds of morphology, and that morphology is by the same hardware based on different tasks. So what's symmetry bringing us? So we in fact ran a very large study that would have more than 500 variations of the robot design. And what you're seeing here is, among all metrics, the Argus design will fulfill the most symmetric version. False text and the programming front almost gets the best performance, while at the same time we want the most symmetric one. And so more of the details will follow in the paper. So as we start right here, we kind of try to think about what are the guiding principles we should follow in robot design.
have a short, quick the questions from audience. Did anyone have a question? Or
I do have a question. Yes, I need to type for our speaker as well because I got the microphone. I wanted to ask about the robot studio class, like how many students participated and if parts of the Duke humanoid were used during the teaching of the class or could be reused during the teaching of the class.
Yeah, thank you. So I heard clearly, so you're asking how many students participated in the robot studio class and how many students were involved in the humanoid.
Right.
So I think typically there are 30 to 40 anywhere students at Duke, and this class is cross-listed between mechanical engineering, electrical computer engineering, and computer science. So we do have like students who were computer science students and never touched a 3D printer ever, being able to build the entire robot from scratch. You know, we only allow people to form a team at maximum with 2 people, but you know, in the 2 years that we talked about this class, you know, the maximum number of people who have formed pair, I think it's like 2 to 3 teams at max, and actually the rest of the whole class is just conducting this with a single student. All of the students, they're all generations, successfully built a robot and participated in the walking and dancing competition. And part of this is really we don't want to rate them based on performance in the walking and dancing competition. I take this as the last lecture, and what we want to see is to let students know how hard it is when you try to deploy sort of learning-based or optimization-based algorithms into a real physical robots and live demo that already works. So that's kind of the lesson they take. And then the next semester, I teach a class of robot learning where we kind of start to introduce more advanced techniques to go there. So some of the students actually took the robot they designed and started to develop the second project on the robot learning class using that platform. And for the Duke humanoid, so students are amazing. So my postdoc, Oshi Xia, so he's the first author. And then the rest we have another 3 anywhere students. The second author is a freshman, and then the others are I think 2 both are junior students. So that's kind of actually both of them were sophomore when they joined the project. So we have a total of 4 people for the humanoid. And for V2, we similarly have 4 people, and then the only difference is like one of the undergraduate graduates and then the other graduate students from the project.
Thank you very much again. Sorry we need to switch because of the time, but let's thank the speaker again.
Okay, so quickly start the next presentation. So I'm the organizer of this workshop, the Kento Kohara-san from the University of Tokyo, Japan, and today I will talk about the MEVIUS series, the open source metal robot hardware easy to assemble. Let's start. So quickly let me introduce myself a little. My name is Kento Kawahara-zuka. The last name is very long, but the 5 A's are included in the one last name. But I'm an assistant professor at the AI Center and the JSK Robotics Laboratory at the University of Tokyo, and the organizer of this workshop. And my research topic from the musculoskeletal humanoids, like the biomimetic robots, and then the biomimetic control of them. But then now I'm going to the more the learning-based control and the foundation model-based robotics. And now we are going to do more about the open source hardware. So this is the talk, the first slide of the talk, of the welcome talk. But yeah, of course, so far the various open source quadruped robots are released in the world. For example, the Stanford Doggo, the Solo 212, the Open Quadruped, the Powder Cube MEVIUS. But I made this kind of MEVIUS now. Okay, so the sound is really. Oh, sorry for that. But yeah, firstly, please watch the motion of the MEVIUS, which I developed. So by using the reinforcement learning and tutorial technique, the MEVIUS can allow us to walk through the obstacles. It's not perfectly stable yet, but it can traverse reasonably the rough terrain. So what is a MEVIUS? So the MEVIUS is the quadruped robot made entirely of metal, and with all parts procurable through e-commerce, especially Misumi, the Japanese company Misumi and MEVI. And yeah, this robot has a minimized number of components. They constructed only with e-commerce metal machining, sheet metal welding, and also shell parts. And all hardware, software, and running environments released as open source. And actually, I think this is the first metal open source quadruped robot in the world. Yeah, the MEVIUS, I will explain about the design overview of MEVIUS. So the one important thing of this is the ultra simple design. Actually, I have designed this robot in just 1 week and assembled in 1 week, and controlled in 2 weeks with the super short. And yeah, I thought I have considered what is the minimal design, what minimal configuration of the legs and the body structure of the robot. And actually, this robot has only 10 basic components used to build the entire wings. So why is this possible? So I'm utilizing the sheet metal welding a lot. So the base ring and the hip ring of the robot, for example, are made from the single sheet metal welded part. So this sheet metal welding can enable the fewer components, strong enough, and easy to assemble. And we can integrate some parts into the one component, and it's easy to assemble. So actually, here we are utilizing the e-commerce and the machining service. Maybe a lot for the MEVIUS. This maybe is the MEVIUS machining service, and it's very easy to use. So by simply uploading the step files, an automatic quotation for metal parts can be generated, and also the important thing for open source robots, the part numbers of the components can be shared. And also I want to say not only machining, but also a lot of the machining service, such kind of the sheet metal welding are supported, and it's easy to use. So as I said, MEVIUS is open source. It means that the bill of materials is open. So all data is publicly available, the step files for each link, assemblies, and URDF. And also, as I said, maybe part numbers for each metal components are included in the bill of materials. So I mean, every component, every part is orderable in just a few clicks. Oh, sorry. So now I'm going to explain a little about the circuit configuration in MEVIUS. So I think it's the simplest circuit configuration using a single channel CAN USB. And it is driven by the 12 voltage logic and the 48 voltage power loop battery. And there is a wireless emergency stop for the MEVIUS. And the translational and rotational velocity is acquired via the RSense T265. Yeah, this is the inside of the MEVIUS. So wireless emergency stop, the power relay, diode, computer, everything is inside of the body. So this is the simple control architecture of the MEVIUS. So the policy is trained by using the ISGIM, and by using the trained policy and common Python scripts, the simulation, the MEVIUS in the visual code, the simulation, and the real world actual robot can work with the same program. So let's see one more time the function of the MEVIUS again. So even with the simple hardware and circuit configuration, the MEVIUS can robustly go through the whole circuit. This is a comparison among the existing robots and the MEVIUS. So the mini cheetah and animal are closed source first two lines, but Solo 12, the sample doggo, PowderQ, and MEVIUS are open source. Among the open source robots, MEVIUS has the largest body weight, length, and maximum torque, and entirely the metal. And after making the MEVIUS public, the several Japanese companies introduced MEVIUS. I know the 5 or 6 companies. For example, our corporation made MEVIUS and used it for the robotics competition. And also MEVIUS is currently available on the market by our corporation. So now, we have some progress for MEVIUS. So the light box meets 360. The LiDAR is mounted facing downwards on MEVIUS, and the elevation mapping is built on Jetson, and the process locomotion via teacher-student policy is teacher-student running is possible now. And this is the result. I was in the ETH a little, and this is the process locomotion using the teacher-student policy. And this is the visualization of rider. So yeah, the steers recognized well, and the MEVIUS successfully traversed the small steers. And yeah, currently the MEVIUS can climb up steers, and even in this kind of very small robot, this robot can traverse a lot of terrain. And currently, not only the robot MEVIUS, but also we are developing the other robots. So I can now share this robot, the middle robot, the crane, and the right part, the MEVITA, the bipedal robot. Firstly, I want to show about the crane. What is crane? The crane is a robot based on the MEVIUS with an additional active waist joint. Another difference lies in the orientation of the legs. While the MEVIUS has its front and rear legs facing the same direction, but the crane's front and rear legs face opposite direction. It's kind of the same configuration with ECMO. And however, the fundamental structure is exactly the same as MEVIUS. So, but why how we made this crane? Yes, so this is for the chimney climbing. So yeah, maybe the Boyan Chen is also doing the chimney climbing with the unique robot, but we are doing the chimney climbing with the quadruped robot now. Yeah, so this robot can adapt to the various widths of the two walls by using the active waist joint. So of course, not only integration, but also this robot can do the chimney climbing by the actual robot. This is amazing. So almost a 20 kilogram quadruped robot can climb up between the two walls, and it was very impressive. And the next one is MEVITA. So what is MEVITA? So this is a metal bipedal robot with all hardware, running algorithm, and software developed released as open source. So I think this is the same with the MEVIUS, but the simplified ordering and assembly through the minimization of the number of components and by sheet metal welding. And body design with all structures, parts procurable via MISMI, and maybe the same with the MEVIUS. And also the robot's working controller based on the reinforcement running and centrifugal technique. Yes, this is the motion of the MEVITA. So yeah, you can make it. Everyone can make it this robot. So please make it. But this robot can walk robustly on the grass, the soil, or sometimes the rough terrain. Yeah. So this video should be very long, but yes, this is a MEVITA. So then we have changed the hardware of the MEVITA. So we have modified the foot of the bipedal robot MEVITA into a ring shape and changed the bipedal robot into the bimanual robot. So because everything is open source, it's very easy. So we are making everything. So changing the foot is very simple and very easy. So now a new MEVITA has 5 DOF arms with wrist joint, so elbow and shoulder joint. So what can we do now? So this robot can do a giant swing. By changing the hardware and front running, this robot can just swing like this. So yes. So this is the conclusion. So I explained about the MEVIUS series and open source the metal robot hardware platform. So the minimized number of components, making extensive use of sheet metal welding, and the free buildable through e-commerce only. And even with the simple hardware and such configuration, the reinforcement running and centrifugal technique enable robust execution of the diverse behaviors. And as open source hardware can be freely modified, the various extensions are possible. So such as the wall climbing with crane and the giant swing with MEVITA. So I think the future of the physical AI will advance through both hardware and software, and open source hardware will become one of its key enablers. Thank you so much.
Thank you very much. questions from the audience? Please line up to the microphones if you have a question, Kento. I do have one question to start us with. What about the data? Do you have some perspective on sharing robot data or
what is robot data? So you mean the
like data sets for locomotion or?
I think it's possible, of course. But I don't know what kind of data is necessary for the locomotion. Yeah, of course, for intentional learning, I think there should be a loaded data set. But yeah, currently I'm doing only the locomotion side, so I don't know. But of course, maybe such kind of the locomotion style can be analyzed for some of the work. I don't know, maybe it should be useful, so I can share it if you want. Yeah, please send off the request.
Okay. Do we have other questions from the audience? All right, so while Thomas sets up, maybe one quick question. Why did you switch to the cross-leg configuration for climbing?
Yeah, of course, changing climbing is really difficult for this kind of road, right? So,
right.
Yeah, so.
Okay.
Yeah, actually only that.
Only that. Gotcha.
Yeah.
Okay, thank you very much again.
Thank you.
And so our last speaker for the morning session is Thomas Flayol. Thomas comes from Las CNRS, and he will tell us today about the journey of the Open Dynamic Robot Initiative, which has been mentioned in other presentations this morning.
So today I'm here to talk to you about the journey about the Open Dynamic Robot Initiative project. So it's a quite old project for this kind of open hardware design for leg robotic. Initially, so it dates back 2018, 2017 maybe. It was initiated by Ludovic Rigetti, Max Planck Institute at the time. And the goal was to provide an open hardware actuator design to build different robots. So it was really about the actuator. It is still a fully open hardware and source software collaborative project. It was a collaboration between Max Planck Institute, the Las CNRS, and the New York University. I want maybe to give you some context of the beginning of this project and the scientific context at the time. So I would say that in the mid-2010s, we saw researchers in academia really wanted to push a shift in leg robotics, going from inverse kinematics and position control robots toward inverse dynamics or more sophisticated force-based control with joint control for the actuation. So, for example, you can see on this robot that we had in my lab, HRP2, for a long time it was used for really position-based tasks, and more we wanted to have inverse dynamics or MPC and be able to be compliant with respect to human interaction or interaction with the environment. In this context, several approaches emerged and matured. One was to add to the existing actuator, like a classical high gearbox ratio actuator, to add the torque sensor to do torque feedback. So you could control, send a command in torque, and it will be feedback by the classical motor plus high gearbox actuator. So a very nice example of this is the DLR design. And here you can see the Toro robot. Another approach, which clearly now dominates, I think, the robot design, for like robotic at least, was this proprioceptive actuation, mainly pushed by MIT, which consists in trying to have as low as possible of gear reduction gearbox to minimize friction and reflected inertia, and to use motors which were more susceptible to provide precise torque given a current and more dense in torque current motor. So kind of the pan-shake shape of the actuator that we see a lot in robotics today. So it was also about 12 years ago that MIT showed this really nice demo for the cheetah leg. And before, with high gearbox robot, you could not hope to be able to kick a leg of a robot like that and to be able to absorb impacts. So very, very interesting for leg robotic research at the time. This project, the open source, the Open Dynamic Robot Initiative, was really about the same time as those developments. And we wanted to apply that and to be able to provide the community with an actuator. So thanks to Felix Remeyer, which was at the time a mechanical engineer at Max Planck Institute. He was a former Boston Dynamics engineer that works a lot with Big Dog. He came up with this design for the mechanics at least, which consists of very small Reportus drone motors, coupled with a low gearbox made out of timing belt and pinions. And this actuator is actually quite simple in terms of bill of materials because it's standard, mostly standard off-the-shelf parts plus a few 3D printed parts. So out of this actuator, we could build a lot of different robots. Also, there was really an effort to document everything in the mechanical, electronical, and software for this project to be reproduced, and I think it has been reproduced quite a lot. Also, a key challenge at the time was to be able to have very compact, because it's still small size robotics, motor controllers. So now we have a lot of options to field-oriented control, but it's really key in this actuator. And often it's not as good implemented as we would like on commercial solution. But basically, at the time, what Max Planck decided to do is to work with off-the-shelf big development board from Texas Instruments, and to have it in a very compact form factor. So thanks to that, and also some electronics to centralize the communication and to be able to control the system with very simple SDK software, we were able to have a standard architecture that can be used on several robots. So I will pass quickly because we cannot always discuss this. Then came all the robots that we were able to construct out of it. There were quite a few at the beginning. We started just with the 8 degrees of freedom simple quadruped robot. And quickly after that, we switched to a fully 12 degrees of freedom robot, Solo 12. So maybe some of you know this robot. But there were also other side projects to build the biped 6 degrees of freedom, or to have some kind of manipulators, or just a leg to do teaching and stuff like that. All sharing the same electronics. I will mainly illustrate those robots by the most advanced one, which is Solo 12. Some results, for example, so this robot is quite old now, but still used in our lab and in many labs. So this is a result that we got for last year at CoRL. So those algorithms evolve very quickly. So it's still, it already looks dated, but we were able to do some kind of parkour motion with Solo 12. So here we had vision, we added autonomy to the robot, also to add battery. It's fully autonomous given the environment and just follow given trajectories. And the work was about how we can train given constraints, but you can refer to the work. What I really liked also about this project is that a lot of people reproduce, of course, the project. Bad Robotics were also a provider of kits to assemble or even to buy a fully assembled robot. But some people took the crazy challenge to make it lower cost and to change parts. So we really saw very nice knockoff that we really like. I would like to say a few words about the current state of the project, because it began quite a long time ago, and a lot of things have changed in what is available commercially, for example. I would say that I would not recommend you to continue to replicate this project for several reasons. For example, first, I think commercial solution, in terms, for example, of quadruped, like a standard 12 degrees of freedom quadruped, makes it quite challenging to justify this build, because it's clearly outperform what we can do with our open source robots. And it's quite also difficult to repair. It's difficult, not because it's complex, quite simple, but you have a lot of wiring, it's all custom, so it's difficult to work with those robots. And a lot of people try to replicate this work, but fail because they didn't have all the infrastructure to properly work on the mechanics. I would say that now you can have more integrated building blocks like actuators, for example, inspired by MIT Cheetah design, that you can then construct robots around, exactly like the previous presentation. And I think that still open source is very, very important in terms of building blocks that we can use to build very different robots. Not standard quadruped, but if you have the idea, for example, the last presentation is a very good illustration out of this concept, but you want to add a spine link, for example, and if you have off the shelf or in your catalog of possible technology, those actuators, for example, or links designs, then it's very, very justified to invest in open source, open hardware robot. I think that we should more custom design our robots together with the controller, so in a kind of co-design manner. And now that we have reinforcement learning as a tool to quickly and quite independently of the platform test the controller, we can also optimize the design. So if you are really committed to optimize the design to have a custom robot for a given task, then it makes a lot of sense to invest time in this development. And also a very, very good aspect of open source design is for teaching. And I personally used a lot this robot for teaching. I will also say a few words about what we are still developing in the initiative. And we are still working a lot on the motor drivers, so we had quite upgrade on this. So now we are to the state where we have a very advanced motor controller, but it can test very crazy algorithm, which I think outperform in terms of compute what is available commercially, and more importantly, we are able on the system to implement whatever we want. So mostly we are not able to modify the firmware of closed source actuator designs. So I will not enter into the specs, but to illustrate that, so there is an only poster there, but maybe it will be moved outside. But one of my students is here, Rafael, you can talk with him. He implemented this crazy idea that we had, that we could do very high bandwidth feedback, linear feedback at 40 kHz, for example, to be able to implement whole body inverse dynamics, for example, or network interpolation of reinforcement learning policies. And this could only be done because we had the custom board designed for this task. So don't hesitate to have a chat with Rafael. I said it, for teaching, it's really a bliss to have those systems where you can really look and analyze at any specific level, from the very low-level control that you can use for teaching control theory and to look at the internal variables, etc., to the mechanics and the system design, up to the control algorithms, communication, etc. So I use it quite extensively for a lot of classes and also together with my colleague. So in that sense, this is a very good way to motivate custom designs. Another news, so we had an attempt to, a bit similarly to the previous work, to upgrade a bit this robot to use off-the-shelf actuators and custom links. So we built this SASA robot, which looks very much like MIT Mini Cheetah, for example, timing belts for the knee, etc. Here we were quite disappointing actually in the actuator offer that we can have. So we modified a bit this actuator and we removed the controller to put our custom electronics. So this design proved to be able to locomote, for example, but actually I would still not recommend to do exactly this design because it's just a standard quadruped. If you want to use those building blocks to build something else, as has been shown before, then it's really interesting. I think generally, this has been said several times this morning, that it's a very, very good time to build robots. So it's true that we have the machining offer to have custom parts very quickly, quite at low prices to be made, even metal machining. So here you can have a small prototype we are working with a PhD student of us in the lab. And also we have all the quite mature additive manufacturing technology that everybody has in lab and in the industry to very quickly iterate. So that's a very, very good time to build robots. Also we have off-the-shelf actuator sensors, which makes this a very, very nice game to play. Thank you very much. If you have any questions.
If you had all the time in the world, what is the next robot that you would like to build?
I would like that the next robot that we build is highly made to run and to do very dynamic motions. So this is a project that we want to do. And to do that, we don't want to do it like a classical mechanical design. We want to have it tested before with locomotion policies, before we even start to think how to implement stuff. Also, I think that for a long time we built robots which were made to be controllable in the classical sense. So we, for example, a long time ago we wanted to have coaxial joints for kinematic arms, just because the inverse kinematics is easy to compute. I think we are still continuing to enforce rigid body dynamics and to have a very precise joint, etc. I think we could get away with, thanks to, for example, reinforcement learning, get away with a lot of those limitations and to build simpler and more robust robots. And also, the co-design is a big motivation to me. And I wanted to be open.
Right. We are sorry for running a little bit late. Let's thank the speaker again.
So this is the last session of this last short of this session, and maybe the lunch box will be provided from the organizers. So I mean from the workshop, from the hall. So I think you can take the lunch box. I don't know where, but.
See you back at 1:30.
So yeah, just
sure.
Okay.
Go for it. Yeah. Yeah, thank you guys all for inviting me. I really love the workshop topic, open source hardware, robot learning. It's great you guys invited me. I want to talk about low-cost hardware, specifically with robot hands, and some of the work we've been doing and how it relates to robot hand design in the past few years. These slides are laggy. Okay. Cool. So, robot manipulation today, a lot of times in research, has been limited to two-finger grippers or suction cups often. However, there are a lot of hands, a lot of interest in hands on humanoids, and we've seen really great locomotion results on our humanoids. However, hands has been much more elementary, and hand is close to half the work actually of engineering for many of these humanoid companies, because it's quite hard to design a hand. There are some virtual robot hands for robot learning. When they come fully assembled, they're often very expensive, they don't have a customizable design, and often they're missing software that robot learning researchers really want. There we go. So what's really happening here is we have some company or mechanical engineering company that'll design a hand for us. They don't necessarily know what the research problems or ideas that we're working on are, and then we buy it and we just hope that our machine learning can work with a robot hand impact. And we're not really customizing the design of the hand in real time. We're iterating between our hand design as well as our robot learning algorithms. So while there are some open source robot hands out there, they're often relatively brittle or they're not high degree enough freedom. And they're not really designed for robots in a machine learning age, which needs to collect a lot of data and run for hours and hours and hours to do successful teleoperations. So there are a few hand design paradigms out there. Often we'll see motors in the joints. So more famously, a Lego hand had these 16 motors in the joints, and they actuate each finger joint directly. You can see this also in newer hands such as Sharpa, where they design the motors smaller so they can make the hand more ergonomic and smaller and easier to do a lot of manipulation. But we've also seen some tendon-driven designs out there. The motors are usually placed in the wrist, and then the tendons actuate the fingers. Now, however, this is fairly expensive and fairly complicated, so we've seen the tendency of people bouncing back and forth between these designs, and not one has been winning. And so the motors as joints paradigm, we've seen a lot of low-cost hands with that. The servos have motors, the gearbox, and angle sensors all packaged together. And the output of the servo shaft directly actuates the motor. It's very simple to understand. So I want to talk about some of the work I've been doing on MEVIUS, which is our low-cost anthropomorphic hand for robot learning, which uses these motors in the joint concept. And MEVIUS is a robot hand designed for machine learning. The hardware is highly dexterous and it's very low cost, and it's very strong and durable. And we have a whole suite of software, and I think the software is what really makes our hardware work. It allows it to be compatible with a lot of different robot learning systems that you may be using today. So if you look at something like the Weber hand, when the fingers are down, the finger twists in place. But when the fingers are up, it moves left to right. Well, this is good for grasping. It's not very human-like, and it's hard to retarget and use with human data. Alternatively, we move the fingers so I can move left and right in the down and up configuration. This is due to moving the MCP side joint after the MCP forward joint. And this is a little more human-like, and it makes it easier to retarget to. It gives us better grasping diversity, and this adduction mechanism gives us much more dexterity on different tasks. And this is really something that we realized when we did a lot of our machine learning experiments and kinematic structure that we improved on. And we did some analysis. What's very important about this is that the fingers and thumbs are posed and we can have a bunch of different pinch grasps. And you can see that the pinch grasp area is larger with our hand versus the baseline Allegro hand. And also the MEVIUS ellipsoid volume is how different ways we can grasp objects is also improved. We also show grasping tests. And it's very low cost, it's very easy to produce. We've seen a lot of hands out there because of how easy it is to build. And the strength tests, we showed that MEVIUS are relatively strong. Strength is really important in your robot learning because we're collecting lots and lots of data and we're teleoperating for long periods of time. And having something that's strong and durable is very useful. This motors in the joint design really facilitates that. And it's also fairly durable over time as well. So, one of the common questions in software is, well, how do you get from human data to robot data? And we have a study called retargeting, and we've done this where we take joints of the human hand and we copy it to the robot hand. We also do some energy function approach, which we also released, which do inverse kinematics, which allows you to optimize for the fingertip position directly. And we use this on a motion capture glove system. Yeah, and the imagine capture glove system where we optimize our fingertips with a human hand to the robot hand. And this allows us to teleoperate a bunch of different tasks successfully using a variety of different lead hands. And we also use Apple Vision Pro to be able to teleoperate our robot hand and release this code on our website as well, which a lot of people have used. While it's less accurate than the man's gloves, the Vision does afford more hands-free, an easier way to teleoperate. We also do something with human video, just using a webcam. Oftentimes when you're on the internet, you only have webcam data. And having some sort of retargeter that works only on one RGB camera is also useful. We also use this on our learning from internet videos as well. And I think one of the great things about motors in the joints is that it's very easy to simulate such a hand. These simulators are really designed for rigid body kinematics, and the lead hand is basically a rigid body kinematic structure. We can create a URDF fairly easily and fairly accurately in these simulation platforms. We've been a very popular hand in academic research today. There's been a great community. It's been great reaching out with all of you and working with so many different people. There's just so many exciting projects going on. I just highlighted a few universities I work with. There's just so many more. It's really great working with everyone. And I think it's great that open source hardware brings this community together on a shared platform like this. However, there's still a gap between a robot hand and a human hand. There's been this great, the hand is too big. There's not really the soft skin that a human hand has. A human, we have a lot of compliance in our hands, and it's very useful. And we have a more dexterous kinematic structure. So, the strength and size issue really comes down to the fact that the high-powered motors are usually large and heavy. And if we want to get inexpensive servos, are even bigger. So, weak hand is going to be 50% bigger than your human hand. And that's just because of the motor design. And compact motors, are often not strong enough, or they're pretty difficult to produce. So if you think about some of your latest hands coming out, like Sharpa, RoboNow, Fujifilm, these hands have motors in the joints, but they have to build custom actuators and custom motors with very small gears, which can be expensive. It's fairly hard for us to get as researchers cheaply. And the motor choice really limits the design of your hand and how you can make your hand work. So there's been this hope in tendon-driven hands, where instead you put the motors in the wrist, and you attach a tendon and pulley system to the fingers. And the tendon is often like a fishing line or a rope, and it pulls on different parts of the fingers. And this is sort of similar analogous to how humans tendons work to move muscle strength from your forearm into your hand. And we see different designs of this where you have like one tendon that pulls on it and a spring that sort of brings your finger back, or you have two tendons, one that pulls and pushes on the finger. So then the question is, well, what joint do you use that you're actuating? And the simplest thing, okay, let's just add a revolute joint, right? You basically have two rigid bodies, and they rotate against each other. And this only allows for 1 degree of freedom rotation, which is sort of a problem because sometimes when you're grasping an object, your fingers will twist and will come in different directions, and that'll cause these fingers to break. You don't want the finger to break off. Rolling joints allow for partial motion in an other than the actuation axis, and we've seen a lot of hands doing this recently, where basically the rolling contact allows the fingers to basically roll when they come in contact with objects and prevents them from breaking. This can be pretty complicated to produce, but it is fairly reliable. And there's one design that really has been fascinating me for a long time. When you think about like the cap on your, on a lotion bottle, you have this plastic hinge. And it's called this flexure joint, this living hinge, and it's the same material throughout. It allows it's just because it's thin, it allows it to bend. And this allows rotation and translation, some other axes other than just the one you're actuating. And it's like pretty easy to produce in 3D print. So I've been spending a lot of time trying to understand, well, how can we make this into a hand? Maybe this is the approach that's really simple and easy to use. So I've been spending time, thinking about rigid hands, and now we're moving towards soft tendon hands. And I think the combination of tendon-driven and soft hands should give us, more reliable and still strong hands. So our first attempt at tendon-driven was, let's just make the fingers completely out of TPU. And what you see in the top right, it's great because you can just bounce the hand on the table and it won't break, and you can do real-world RL and all sorts of stuff with it. But the downside is this finger is pretty soft, and it's almost too soft. Well, you can do some retensioning and calibration in software to try to basically make the finger behave better. It still will be very, very soft. You see, we do some real-world RL with it, where we're grasping grapes or a spoon with grapes on it, a bit of both. So this flat palm also leads to bad grasping. One of the things we found, look at the hammer inside the fingers, it's sitting there, but it's sort of not really against the palm like you want it to with a human hand. Well, you can add an articulation in the palm, which we do. We've also found different ways to get around this by making the palm smaller. So with all this findings, I'm thinking, okay, let's make a new hand, let's make it stronger, let's make the palm better. And one of the things that really inspired me is this idea of like the human hand, you have bones and the skins, and the bones make your fingers really stiff, and then that skin is sort of outside compliance. And what we did is make this robot finger you can see on the right, which emulates that. So there's this outer skin, and then the interior white bone structure inside. And the outer skin is TPU, but the internal is PLA. And you can 3D print this pretty easily on any regular 3D printer. So the nice thing about this is you still get that, that durability. You see bouncing the hand on the table, the fingers don't break. But at the same time, is when you try to twist it on the bottom right, it's harder to twist it. And that's because the internal bone structure is preventing that twist and it from basically crushing down the finger. It's giving it a lot of strength. And there's also this, this other thing with tendons is that under actuation. So actually, we have one motor and one tendon actuating the MCP with the dip, which is your 3 curl joints in your finger. And by doing this under actuation, we have to design, well, where does this where do the fingers actually land? And what we do is we optimize it for the pinch grafts to be pretty strong between the thumb and the fingers. So you see on the bottom right, the hand is actually able to do pinch between the thumb and all 3 other fingers, even if there's only one motor in each finger. And that's due to the under actuation design and also how soft we're making the TPU material. So essentially, the MCP joint, the base joint, is actually the weakest one, so it actuates the most with the tendon pulling down on it. And then we also have the MCP joint from Lipan V1. I really like the motor underneath the finger. Well, maybe it's not the prettiest thing. You don't have to worry about tendons. The more tendons you have, the more you have to calibrate, the more it can break. And this MCP joint, this dexterous MCP joint, really, there's nothing to break, and the motor's just underneath the finger, and it's really very reliable. So in total, we have 8 degrees of freedom then. So this costs like $200. This is actually the first time I'm presenting this hand at the workshop here. It's $200, and it's 8 VTech motors. It's really easy to produce. I have all the assembly instructions on my website. As you can see next to my hand, it's actually a little bit smaller, which is great. And the palm is nice and small. And really, it requires less than 50 screws, and that's because the finger and the palm are each one piece. So the 3D printer basically does all the work for you. You just have to slot the motors in, and then push a tendon through a hole, and then tie it down, and you're basically done. So you can really assemble this as easy as you install a Jello or something like that, or even easier. So I got this working just a couple days before Coral, so I'm really excited to share this. This is our first video of us using the hand. So this is we have an ARX arm set up here, just teleoperation with Jello and NS bugs. I'm super excited that we were able to get this bimanual system working, and it's very, very inexpensive. So those ARX arms are around $3,000, each of the hands are around $200, and then you just need a Jello and some sort of glove to teleoperate. And I think what's really cool is that with the under actuation, well, first of all, the hand is so light because of the under actuation that you can actually put this on an ARX arm, which is like $3,000. The second thing is because it's under actuated, you can actually still, grasp a plate in the corner here, and it'll still grasp well, actually, because of the compliance. And the other great thing is when you see picking up the kitchen utensil, is that the fingers curl really tightly, and that's because of the multi-material fingers. So I think the combination of these multi-material fingers grasp curling tightly, the lightness of it to be able to put on an ARX arm, being very inexpensive, and showing tasks like plates or kitchen utensils, which are really, really hard. I think I was very, very happy with this, and really excited about this direction. So I'm really excited to spend more time with this hand on this sort of approach. So we've also been looking at more advanced versions of this, where maybe you don't want this under actuation too much. So sometimes the under actuation is hard to simulate with other things like that. So we make an advanced version of the hand, which has articulations in the palm. And this articulations in the palm and the articulated independent MCP joints gives it a little bit more strength, with the downside of being heavier and have more motors, and it's a little bit harder to assemble. And this articulation in the palm, see this video here on the top right. So you see the video on the top right, the articulation in the palm allow the hand to basically independently pull the fingers closer together. And that pulling the fingers closer together is really useful for getting better and better pinch grasps. Those pinch grasps are really useful to grasp around tools or grasp really small objects close carefully. So we showed this on the teleoperation approach. We showed this last year at Coral, where we have this Jello system as well as a manus bug attached to the head. Actually, this allows us to track the arm really well with the Jello, and then the Manus gives us really good fingertip tracking. It allows us to grasp a bunch of different objects successfully. We show a bunch of different results with this. These hands are still only a few $1,000s, and the high degree of freedom allows you to do some tasks that may be difficult for you to do before versus the other hand. And of course, the only under actuation you have is now the tip and dip, and the MCP is actually a motor underneath. So you have a little bit less under actuation here, and it's a little bit heavier. So we need like a full-size arm. But it's still like under $30,000 for the whole system. Great, so we also do some human video, behavior coding with it. I think I'm running out of time, so I'll skip through these quickly. But we see that, these fingers are actually fairly reliable. I think people are always worried, oh, are the flexor joints, going to degrade over time? And we found with the material that we're using, which is Filaflex, that the actual material is pretty consistent. Even like months and months after, the finger keeps performing pretty much just as well as it did before. I mean, if you ever had a problem, you could 3D print another one in theory, but we've never really had that problem. And we've been scaling up our data collection. So this is people wearing Manus gloves in the wild. We have a bunch of different teleoperators collecting a bunch of data in different environments. And this allows us to train behavior coding policies that work in any environment. So this is our hands again on this mobile platform doing a different task, such as putting flowers in a vase or putting them objects. Yeah, so we talked a little bit about this idea of motor-driven hands versus tendon-driven hands, and some low-cost versions of the hands that exist out there that we can build yourself and you can iterate on easily in academia. So LeapHand V1 is very strong and anthropomorphic. It's great for rigid body simulation, and it's really simple to control. It's a little bit big, but it's super easy to build, and it's $2,000. And our newest LeapHand V2, which we're just talking about today, has really small kinematics. It's nice and human hand size. And I really like, the ability to pick up plates or small kitchen utensils that were difficult to do before. And the under actuation, if you embrace it, really gives you this great, strong finger that can just last for a long time. And it only costs a few $100s, and you can 3D print it on any regular 3D printer. Yeah, so that's my talk. I guess, do we have time for questions?
Yeah, thank you.
Thank you for the very great talk. So, is there any question from the audience? If you use a microphone around there. You have a question?
Thank you for your presentations. It was great, and I think. So I heard the printing is quite hard to LeapHand version 2, right? So do you have any plan to sell it or make it yourself?
So multi-material 3D printing in the past has been pretty rare because like Bamboo AMS can now handle it. But newer 3D printers like the new Snapmaker, I think it's U1, the new Bamboo that came out recently, and also Prusa XL can all 3D print this hand pretty easily. So I think that argument has gone away. It's actually pretty easy to 3D print now. I do release like 3MF files, it's called, because there's so many settings, and like you want each joint to be a different stiffness and infill levels and flow rate, that you basically need like a whole 3MF setting, which is basically all the settings you would need to import it into your slicer and print it yourself. So I provide like all of those settings. I don't have plans to sell it. Maybe if someone has a 3D printer farm and wants to talk to me about getting these out there, I'm happy to collaborate on something like that if people want that. Yeah.
Is there any question? Matt?
Instead of like using multiple materials, 3D printing, is there a use for like topology optimization, sort of optimize the internal structure of the fingers and maybe like make them bend in one direction, or like sort of change the structure, like the behavior?
Yeah, so there's already a lot of optimization. I didn't go into the details, obviously, in a 20-minute talk. Like, you're right. So, like, one of the things you worry about is, like, how much do you twist on this axis? And actually, what the settings in the 3D printer file does is it makes this side and this side the highest infill and also the stiffest. So it resists that twisting around the central axis. And you'll see also, like, the multi-material helps with the crushing. So, if I push down on the finger, it won't just, like, crumple up. And I think you really need the multi-material to do that. The other thing that PLA multi-material is giving you is the tendon slide easily across PLA, which is on TPU it won't. And the TPU will actually start to basically degrade and the tendon will start cutting through the TPU over time. So the PLA actually is, I think, sort of necessary to keep the finger rigid. Yeah.
Okay. Thank you.
Hopefully that helps.
Yeah. Thank you so much for the speaker again. Okay, so the next speaker, the next speaker is Yuki Nakagawa from the RT Corporation Japan, and towards safe coexistence, risk assessment and safety design of the open source hardware.
Zoom に入ってもらって、Zoom リンクってもらって。OK です。
Okay, hello everyone. So I'm Yuki Nakagawa from RT Corporation. So our company is in Japan, and I am an OS director. So how many people uses the loss? Okay, thank you. Yeah, so I'm director of the OS. So we use many hardware using the loss. And then our company, I led this company in 2005. And then my company have two divisions. One is an R&D and training using the AI and robotics. And the other one is individual factory, industrial, how to say it? So we apply the AI for the industrial robots and making factory automation. So using AI and robotics. So we collaborate with a software company we develop the hardware, and we collaborate with a software company, we provide hardware, and for end user, we provide everything, hardware, software, AI, everything. And also manufacturer, collaborate with manufacturer, we are supported with the laws, how to make a laws or how to make a loss model. And also, we also have a training for the academia and or industrial use. So one of our food factory product is a humanoid. So please see that. So you can see a small humanoid robot and two in front of the meatball bucket, and they picking one by one to put the cans. And this robot is really installed into the food factory. So we provide a prototype of this robot named Shuras. They will be hardware for the educational purpose only, because for the disk management. And also this is working with an individual booth. But next one, so you see, this is also the lunchbox line, and this robot be in line with next to the next human. So we think that we need keep safety to collaborate with the human. So you can see that this robot is very close to human. Yeah, so we make such a robot for the food factory. Okay, let's see. So So you know that Japan had an expo right now, and they have such an exhibition. So this robot and hug with small children, like this. So inside is not human but a robot. So you can see that we have to keep the safety to contact with the human. So we think that importance to make a hardware as a risk, how to avoid the risk. Well, so we sell original robot for the academic purpose, for the research and training, something like that. So small wheeled robots and small robot arm and a small, how to say, you can see that. Sorry. So you can see this is a white one. It's a robot arm. We make it an open source for the educational purpose. But if you want to sell, you cannot use a license because to keep us safety. And also we developed many sizes of the humanoids. So Sukura, you can see the big one. Big one is inside such a robot. And also 130 and 150 and 70. So everything is we developed. But some of them, Tolman. So you can see that Kawahara Sensei has MEVIUS, and one is Tolman, and one is Aloha. So we sell to the researchers. And we think about what is the problem. Because of safety, MEVIUS is for the researcher, I think. And also Tolman is also researchers. So it is very high. And we have to wear something safety shoes and safety hand glove, something like that. And also Aloha is also slightly dangerous for the ordinary purpose. So we think about how to keep the safety for the open hardware. So do you know who has the responsibility to sell these robots? So designer or contributor has no responsibility. So open source software is not need to keep safety because the PC is a PC. So they don't have everything, they don't have the materials, then for the building or something like that. But the robots, they are the physical things. So we have a product liability law in every country. And also a constructor or developer has a responsibility. And also seller and importer is also have a responsibility. So if you provide information with the GitHub, the Hugging Face, something like that, but it is no responsibility. But if you make robots or sell the robots, you have a responsibility. So in this case, so we make many open hardware, and we sometimes redesign for the because of the safety. So open source hardware become a backbone of the innovation of the AI robots. So physical AI and model-based development. And we have to think about what is good for them. So then we challenge the implementation challenge. So the first one is an idea and design. So you think you have a good idea to make an open hardware robot. And this is a level of the idea, but design with a method of the AI. So I mean that model-based development. So if you make a model-based development, making a CAD, making a model, and input into the simulators. And we get some gaps in the real and the simulator. And we found something problem in the simulator. We make it, we back to the design with a CAD or something like that. So, but there's no considering about the legal uncertainty and how to keep safety. So, we think this is a dangerous one. So, sense of the crisis. So, build up from GitHub. We say, I said about our product is restricted educational purpose only because of keep the safety. But GitHub or Hugging Face has no restriction to rebuild the hardware. So in this case, so no suggestion to safety, no suggestion of how to build up or how to aware the dangerous or something like that. So it is a big issue for them. In fact, in Japan, we have many users about four-legged robot in China, for example, Unity or something like that. And some of the AI and the software people have injured with development. So it is not good for the AI community. And also, if you want to sell the robots, you build up from the open hardware, and risk assessment report need to sell the users. And but you are not a designer, so you don't know what is the risk management or risk. And we should give such a report about the risk assessment. What is the risk? What is the dangerous one? How to use or something like that. So we try to how to develop and publish with such an open hardware. And so we tried what is good for the academic. So academic need reproducibility because they want to try to the algorithms, try to the method or something like that, and then they find a new their own original one. So they need a standardized safety and such a good point. And you need a documentation, of course, a risk assessment reports, and what is the failure analysis, so what is the long one, what is the dangerous one, and what is the good one. And also, if we have a peer review system, safety design, you mentioned that this is dangerous, or you can keep safety if you do something somewhat. And also, designer must think about what is a dangerous one. So, summarize. So, software versus hardware. So, that is the difference. So, software failures not harm anything. So, first is just a data loss, performance degradation, security, and rollback possible. So, but if your hardware failure, physical injury, so worst case is a death, and property damage, and death is famous damage is one, and floor, building, everything, and environmental one, and then permanent consequence. So software bug is recover with everything. Many people contribute on how to fix it. But hardware design is very hard because some of them hard black box. What is the concept of the mechanical one? What is the concept of the electrical one? So if made by an amateur, so they don't have any skills, any knowledge of the hardware and electricity and mechanical one, so it could lead a disaster easily. So physical risks are real. So moving parts and the thermal hazard and the electrical hazards, so many things. So some of them they lead big issues, and developed what is good for such a risk assessment with an open source hardware. So according to the AI robot implementation, I mean that model-based development. So you see, so this is a very famous one, Isaac. So we tried with we completed a CAD model. Why not coming? So now my screen has an Isaac screen. So it is very usual to use a simulator if we completed CAD. And then if we have the program with such a simulator, so we work to the CAD design. And iteration of such a CAD simulator, and then we deployment in the real hardware. So how to keep a safety such a model-based? This is just a risk assessment. So we have many ISO and the GIS and some papers. So they show the risk assessment for such a system. So for example, so we need a space with an beam. So it's 25 millimeters or something. These gift beams. So because we have to keep not running away, or how to keep spaces for if not leaves comes in like that, it's pinches. So it pinches is very good case, but bad case is cutting the fingers. So we put such spaces and how to keep them running out, something like that. And also we tested electricity one, batteries and board, and how to keep the board, heat up, something like that. And then we deploy with everything. And then we deploy such a hardware. This is just a bus of the robot. It's just assembled it up. And then we install the software and then push it to the switch. So this robot will work very easy. Yeah. So it will work very fast. So you can see this robot can develop by only 3 months. So first month we iterate on CAD model-based, and using simulators, and then we get hardware and assemble it, and then it's working very fast. So we support risk assessment framework and how to get information about hazard. So first one is hazard identification. What is the risks? So pinches or cutting or running out or something like that. And then how big issues for that each hazard or risks. And then we think about mitigation strategies. So to keep the space to keep electricity, to keep the software or operation. So operation is very important thing, and you can make a documentation how to keep the safety with this robot. So we support building a safe structure for the community of the open hardware, especially for the AI people or battery running. Sorry, battery is running out. Sorry for the talking. So we support an AI community how to building hardware. So basement is the foundational research. So what is the risks? And forward education and training, how to keep their safety. Because the humanoid and the big one needs to keep a safety because they are very, very big and it is not good for the keep a safety. So if you, well, in my experience, so almost 20 years ago, I operated in the Ashmo, and that's 130 centimeters humanoid, and we had some accident, and I stopped the robot. That robot kicks me, and I get on my knees and some injuries. So, but education, so to keep away the space from the robot and the humanoid, very, very good solution for that fast switch on. But after that, they need to cross the space and or touch the robot, something like that. So education and training is avoid an accident. And tool and resources. So if we have an testing equipment or databases and knowledge, so it's based on industrial robot has such a tools. So you should use such a tools. And we make a standards for the open source hardware. And last one is we make a community culture how to keep the safety, because the dangerous one is not good for the social implementation. So for the researchers it is good, and the researchers has injured, but not open for the social things. But users is not good for such a bad, no information about the bad thing or dangerous one. So we should make a community culture. If you are a publisher, if you are a designer, you must be in risk management for that and think about the users. Yes, so this is our responsibility. If you make robots, if you open the information, if you build, if you sell, so please start today and build together and make a community consensus. Yeah, thank you very much.
Thanks so much. So is there any question? So actually the really delayed. So I think we can have the one quick question from audience.
large open source role now. So
our company?
Yeah, but your company or is there any message to the open source hardware developers or how to make do the risk assessment from ourselves?
Yeah, so first one is how to avoid an injury, because our users has no information about what is the risk. So how to know that a robot moves? Almost GitHub has no video. So if your robot is running out perform something like that, so you should I think my recommendation is open the video in the accident case.
Okay. Making such kind of video complicated. Okay, thank you so much.
Thank you.
So the next speaker is the Antin Dapin from the online. So can you share your screen? Please stop your sharing. Please stop sharing. Okay. Hi, can you hear me? The admin.
そうですね。
Hi, can you hear me? It's muted. Yes. Is that mute?
Hello?
Hello? I can hear you. Okay. Yeah, if you prepare please start the presentation.
So Anton Arnefin is finishing his PhD at DLR, and during his studies he has the stable baseline 3 library, which is much used for reinforcement learning and reinforcement learning algorithms. And I believe he has quite a technical Linux setup, which can sometimes be hard.
なんかおかしいな。
Maybe Grégoire, we want to switch to the next speaker in the meantime.
Start sharing.
Maybe wait for.
So he has to stop sharing. Yes.
Yeah.
Okay, listening is fine. So, hello everybody. My name is Grégoire Passot. I'm from the University of Bordeaux in France. The team Roban. Just wait. Okay, I'm going to give a presentation about the robot Simavan, which is a humanoid robot we've been developing, and I will focus a little bit as well on tools and all other projects that we developed along the way. So I will present the robot architecture and history, focus a little bit on perception and then reinforcement learning work. I also have a very short sponsor talk at the end of this presentation as a robot soccer kit project, which also turns out to be an open source hardware project. This is Simavan. It's a 70 centimeter or 7.8 kg robot. It is actuated with a dynamic cell actuator, which are very similar to the toddler robot we saw this morning. So 12 for the lower body, 8 for the upper body. The computation is achieved on board. So the robot has to be fully autonomous, everything is embedded. So it's Intel Core i5 in an Intel NUC with another custom low-level board running on STM32 for low-level bridging and computation. About the sensors, robot is equipped with Ethernet camera, which is a Blackfly gigabit Ethernet camera, only one IMU, and custom pressure sensor below the feet. The parts of the robots are mostly CNC milled, so they are mostly, the robot is mostly made of plain grade aluminium. And there are some minor 3D printed parts, like these bumpers you can see on the body, which are made of TPU to protect the robot's handling. And it is powered by a small 4cell LiPo battery. The Simavan has been developed in the scope of competing to the RoboCup kit-size soccer league. So it's a robot made to compete in this particular competition, tailored for this competition. We've been working on many iterations of this robot. So RoboCup is a competition we've been participating for roughly more than 10 years now. We won the competition 5 times with the platform Simavan. So there is a small part of the game back in 2023. So you can see small footage. So it's 4 robots versus 4 robots, and they have to play soccer games in an autonomous manner. So they have to take decisions. They have to walk, kick, stand up because they fall all the time. So robustness is a big concern when competing in such a league, because it's a very harsh benchmark for your robot. You push each other, fall all the time. There are some soccer games, and there are also some technical challenges. So, for example, example, here a robot is performing a pass with a on-the-fly kick performed by the other robots. So those are examples of technical challenges you can address that are not easy to implement in the games themselves, but are good challenges for the competitor to work on. So the robot is modeled on using OnShape as a CAD, and we also, along the way, we developed a tool that is called OnShape Robot to make easier the traduction and translation from the CAD software directly to URDF, SDF, and more recently natively NuJoCode. So here you can see Simaban being imported in NuJoCode directly from the CAD software. So it's a very active project currently developed in my team. With a lot of features and with the recent refactor, it's way much easier to add your own processor on the way of the import project process. For example, if you want to tweak the parts to change some parameters or approximate some shape on the way, you could plug your code in the middle of the import process from Object Robots. We also have some kind of Swiss tool library called Blaco, which is built on the top of Pinocchio and iQuadProg. That is mostly a tool made for formulating quadratic programming problems. So this is also highly documented now. For example, we have an abstraction layer to formulate inverse kinematics problems, just like Pink, for those who know Pink from Stefan. Here, all the examples you see here are examples from the documentation where you can load your URDF robot, formulate your inverse kinematic tasks, and ask for Blaco to solve them. The big quadrupedal robot you see on the left is a project from one of my colleagues that is actually built. You can see my colleague in the top of the Megabot robot, which inverse kinematics is achieved using Blaco. So both tools, Object Robot and Blaco, for example, are a very good combination to iterate from a CAD to a robot that you can actually control very quickly. We also implemented a very classical wall-quarter generator, which includes planning the center of mass using a classical Kajita approach in Blaco. That is available, and this is now used for limitation learning that I will speak a little bit about it later. When we worked on the robots, we saw that one thing that was missing was the ability to sense pressure. And this is kind of old now, it's 10 years ago. We designed those low-cost pressure sensors that we featured under the feet of our robots. And people in the league started, some people started imitating us and building a form of this project. It is also open source hardware. And can be daisy-chained on the dynamic set bus. So this is convenient in this type of architecture. Especially, for example, if you want to perform odometry on the robot. So this is an example where the robot is entirely blind. So there is no camera, no vision here. And we ask the robot to go back and forth on this penalty arc that is 3 meters roughly away from the center of the field. And you can see that the drift is very small actually. So odometry is a very important prior in this type of robot for localization. We use YOLO in the competition for image processing. Just to give a rough idea, we use OpenVINO runtime to accelerate the inference, with OpenVINO being able to take advantage of Intel GPU. From our experience, Intel GPU is actually pretty good. So you really don't need NVIDIA GPU to infer your YOLO. It takes like 17 milliseconds, something like that, to infer one image on the Intel NUC, and you don't need any extra hardware. So it's a good runtime. In the current state of what we do for localization, we use a lot of features that are detected using YOLO, and classical particle filter. So you can see here some kidnapping example where I just move the robot away in some other position in the field, and the filter diverge and converge again to the new position, and for the robot to localize it. We also been doing some reinforcement learning on the robot. So very recently, we've been able to run a wall controller based on reinforcement learning. We worked a lot with Antoine and took advantage of his work on imitation learning and the mini-duck before this summer competition to port Mujoko Playground walk on the Sigma Ball platform. So you can see here a very short footage of push recovery ability that we can get using this approach. So this is a classical Mujoko Playground plus PPO and imitation reward implemented by Antoine based on reference trajectories produced by Blago with a classical planning approaches. We also use reinforcement learning to plan the footsteps on the robots. So the planning the footsteps is achieved using an external, very small agent that is just working on the geometrical problem of deciding which footstep to take. Actually, this agent, the goal of this agent is to minimize the number of steps you will take to get in position, for example, with respect to the ball that you want to kick. So you have to perform sometimes this type of maneuver to walk around the ball, and it really depends on the capacities of your robot. And when we train footstep net, we end up with an actor that we can deploy on the robots, but we also end up with a critic network that we use for forecasting ability. So forecasting means that given target pose you want to reach with your robots, you can estimate the number of footsteps that will be necessary without even doing a whole rollout of the trajectory, because you can still use this residual critic as forecasting. And in the robots, at some strategical layer, we use extensively this forecasting so that we can compare candidate position strategically to take the one that will just need less footsteps to reach the position. So give us some kind of forecasting ability as well. Here is an example of footstep net plus combined with reinforcement learning wall. Here the robot is walking, maybe you don't see it very well, but the planned footsteps are being shown here on this area on the video. And the planned footsteps are executed by the reinforcement learning agent that is controlling directly the motors here of the robot. And what's good with this pattern is that we can also train different footsteps net. So we can separate and different footstep nets depending on the ability, the presence of obstacles, so that we don't have to retrain the whole motor controller every time. We keep the same working pattern generator. We also worked on more custom stand-up agents. So here I'm just showing, maybe you don't see the video clearly, I'm sorry, but I'm just showing some examples of clear results we had. Before we made through a sim-to-real effort. So mostly the takeaway of what we did is a lot of modeling in all the delays in the chain. So delay for the sensor, delay for applying the actions and so on. There was a lot of improvement on the reward structure. We can talk more about that if you want later. And also a lot of work on better system identification. It was also important. I will talk a little bit later as well. So we ended up with Frasa that was published as well and it's available as well as an open source separate repository. Frasa is a very simple reward structure. Actually, it transfers quite well on the robot. and it's learning using an off-policy algorithm in MuJoCo running only on CPU. So we don't use massive parallelization like what we do in usual NGX, for example, training setup like in MuJoCo playground. And the training is still quite fast. It's like less than 30 minutes usually to train such an agent. So the interest of Frasa is that Frasa can handle the standing up of the robot, but also recovering from strong push, because we just switched from the wall policy to the fall recovery policy. Actually, we have both agents, and we switch from one policy to another. And Frasa can also be used to recover from push before the robot is even fallen on the ground. So some behavior emerges, like using your arm to recover before you even are fully fallen on the ground. And the reinforcement learned work with Frasa was the package we used during the last competition, this summer. Also, so in the process of reducing sim to real, we performed some system identification. So we did a lot of experiments on the actuators, and we noticed that there was some very important phenomenon that was not taken in account in classical simulator like MuJoCo or Isaac. In particular, one very noticeable simulator in high reduction actuators, like the one we are using currently, is the load-dependent friction effect. So, if you apply an external torque to the motor, such as gravity in a pendulum setup like this one, and you apply torque on the motor to compensate, for example, for gravity, you can explore the whole range where actually every motion is stopped by friction. This gives you the type of plots you can see on the bottom left. And what you see is that the lines are not parallel, they cannot diverge, meaning that the more effort is applied inside the gearbox, the more friction, static friction, so the equivalent of high friction, is actually important. This phenomenon is classically not implemented in dynamic simulator. So in a recent paper as well, we demonstrated that we can, on the top of MuJoCo, by adjusting the static friction that is used in computation, we can get better simulation results by accounting for the load dependence factor that is very significant in this type of actuator. So we did this with dynamic cell motor, but also with harmonic reduction actuators. We ended up with another repository that is called BAM, Better Actuator Model, which provides some tools for simple system identification, taking account some extended friction models like this one. So some conclusion and perspectives. So we want to move away from high reduction actuators. As you may guess, the tendency for example, in the league goes in that direction. Mostly the problem is that it's harder to model. So as I said, there are some weird friction and appearing, but also backlash that is harder to model. This is the first reduction and gears is the first breakage source in our robots currently. So the first thing that breaks is basically gears. And it's not that cheap if you consider dynamic cell and compare it with recent quasi-direct drive by KX, R&D, or LGBot. The price is not very much lower for dynamic cell counterpart. And recently as well, if you consider the RoboCup, there is some kind of a paradigm shift oriented to the use of the extensive use of commercial hardware for namely unitary and booster robots are extensively used by competitors, moving the competition to a kind of software-only developing competition. So there are advantages of that. Here you can see, for example, the booster K1 that costs something like $10,000, so it's very hard to compete. So there are advantages. Of course, you can delegate the mechanical design manufacturing to external companies and focus on high-level software and control. This is what a good performing team were doing actually this summer in last competition on Euro Cup. But there is also a risk of dependency to a manufacturer, a loss of mechanical knowledge, and you get less customizable robots. So it's kind of the trade-off Thomas was presenting before. We really hope that we can get a better of both worlds, so having, for example, well-documented actuators that we can build the architecture on the top and keep open source robots that we can customize. We are hiring, so do not hesitate to contact me if you want to design humanoid robots and whatever status you are, so for a PhD student, postdoctoral, visiting scholar, or intern. We have a good term, good facilities, and some ads for the team. I can take a few questions. I don't know after before the sponsor talk, or I don't know, maybe I finish and ask a question after. Stefan can talk, I think. Do I even roll the slides, or do I take questions before?
Maybe let's take questions first for your talk. Thank you for the presentation. All right. Do we have questions from the audience?
Thank you for your talk and sharing information about the local cup and the open source of the hardware. And will you continue to implement this kit-size robot?
Okay, so actually there is a big change ongoing in the league, in the whole league, and a lot of leagues are merging, and a lot of things are being reconsidered currently. So it truly depends on how the rules are going to evolve in the future. So they are talking about the league merge currently. I'm not sure if kit-size league will still exist in a few months. It's not clear actually. So it's a follow-up. My personal opinion is that I truly want the league to continue to exist, kit size versus adjunct size. And the reason for kit size is the one that was invoked earlier by Stanford for Toddler, is that it's cheaper, it's less dangerous as well to operate. For example, booster K1, K1 that I showed, there is the adjunct size counterpart, the T1, that is more expensive, but also more dangerous. And I really feel we can perform good research on the K1 that is, of course, that could be ported to the T1 transparently, but with less dangerosity. I feel way much safer operating a K1 alone than the T1 alone, for example. So I really hope for this reason that kit size will continue to exist. Yes.
Okay, so obviously, I don't know that if the kit community keeps another kit size or does you want the kit size or similar?
Currently, there is kit size and adjunct size in the same competition. So it's soccer, kit and adjunct. Kit is below 1 meter and adjunct is above 1 meter.
Okay, thank you.
Thank you, Grégoire. So we will see after the presentation, and then Grégoire, you can come back to tell us about RSA.
Okay.
Thank you very much. Yes, it works. Thank you.
Perfect. So, thank you for the invitation, and now I would like to talk about designing robot software that is easy to use. So as a bit of a background about where I come from, so I'm mostly working on real robots, so they're trying to learn directly on real robots. And one of the examples is recently we had a mission with the International Space Station, where we had our little quadruped Bert here. We pretended that we had a failure, so that it would only walk with 3 legs, and we asked the astronaut to retrain the robot directly from space in only some minutes. And luckily, he managed, and then we could continue and explore the cave in that So that's the background for what I'm doing, and also I'm also maintaining the stable baseline 3 library, which provides reliable RL implementations. So that in very few lines of code you can declare or you can instantiate different RL algorithm and train it on different environment, and then later save it and load it to query it for actions. And my motivation for today is I've seen when I look at the program there was a lot of hardware presentation. My presentation would be more about software, would be more about what would be my dream software if someone gives me a new hardware. And my motivation for that is hardware are very pretty object, but hardware without software is like an instrument without a musician, so it's a bit useless. So you need to also care quite a lot about software when providing open source hardware. And I would like to give you some tips from my experience of building both the RL library, but also working with real robots during my PhD. And for that, I will focus on 3 key aspects. I don't have the time to fully extend to every aspect, but I would like to focus on first, how to provide high quality software, then how to make your interface more intuitive, and then discuss design decision, which is about modularity, so choosing between a modular versus a minimal design. And all of those apply for open source hardware, but also apply for other cases of software. So the first thing is, when you provide software to your users, you need to make sure that it's of quite good quality, because even though you have a very intuitive interface that is easy to use, that is easy to install, if it doesn't work, then it's also useless. And it's also very frustrating for the user to debug code that they didn't write. And so for that, you have different strategies to make sure that your software works and also follow as a higher standard. One is, of course, to follow the software's best practices, which means that testing as much as possible. So with hardware, it's a bit difficult, but in practice, you can mock your hardware. So you can pretend that your hardware is there, and then you can test about your software without your hardware. I can talk about that a bit later. Make sure to type your API, because especially if you're using Python, because you don't always have time to document, but already giving some types about what is expected and what not already helps a lot the user to know how do you use this method in your API. Another thing is if you have big dependency like ROS, and that most of your software actually doesn't depend on ROS, without it, try to make it optional, because this will make your software more easy to install, and you will only provide the big ROS installation for the one that really wants it, really needs it. As a general rule, try to avoid breaking changes, although you might have very good reason to change to break the code, because it's always provides some frustration for the user. So when you're developing the software for the very first time and you're not yet in beta, it's okay to iterate very quickly, but as soon as you're a bit more public, as soon as you're advertising a bit more your software, you should be very careful and always try to provide some migration guides to whenever you break something in your code. Again, this will prevent some frustration from the user, and actually recently I had this problem where I was debugging code I didn't write, and I had to upgrade code frequently to continue to be able to use the robot. And the last thing is try to document as much as possible. In the sense that I've seen when I look at all the different implementation, there's a lot of documentation about how to build the hardware, how to build the open source hardware, but usually the documentation about the software is very limited. So the next thing I would like to talk about after providing some tips on how to make your software of good quality is how can you improve as a side remark, for example, actually for the Stable's baseline 3 library, we had the problem that it was too easy to use, too simple to use, and so we had people using the library, although they had no idea about reinforcement learning, and then of course they were complaining or they were not understanding the problem they had. So we had to add a key warning in our README because the library was too easy to use. So one thing that can make the interface easy to use is to have a consistent interface. As a bad example, you might know about TensorFlow 1. And for TensorFlow 1, you always had like 3-4 ways of doing the same thing, and you never knew which one you should use. Here on the left, you have an example of just creating a fully connected layer for a neural network, and you can use a TF.layers API, you can use a TF.contrib API, and you can use a TF.keras API. They are more or less the same, but they don't have the same name, they are not exactly used the same way, so it's a bit confusing if you look at it. On the other side, I've got the example of the stable baseline 3 library, and it's JAX equivalent, so it's a rewrite instead of using PyTorch, using JAX and just-in-time compilation. And you can see here, you can really switch between algorithms very easily because they both share the same base interface. And you can even switch between libraries, you can switch between complete backend without any problem. And all the code that I'm showing here is actually working and working the same way. Another aspect to make your interface more intuitive is to think about which abstraction level that you need. So it actually depends on what your user you are targeting. And when I was preparing this talk and looking again at all the open source hardware presented in this workshop, so I did my own homework and had a look at everything that was presented in this workshop, I realized that usually there was two extremes. So usually people were either giving access to a low-level API, so this is what I'm showing here, where just to remove all joint, you will need to manually do a follow, you will need to set the correct mode to position control, you will need maybe to take ownership of each joint and be careful about it. And on the other end of the spectrum, so there was some code base for providing that, and on the other end of the spectrum, you have just a reinforcement learning interface with very little freedom and providing just an environment interface where you can just send some action to the environment and go for some observation. But here there's no flexibility, and the problem with low-level API that is there's a lot of things to do manually, and you need to know quite a lot about that. So usually what I like with robots is to have something in between. And for instance, this is more or less the interface that I'm using for the bear quadruped that I showed in the beginning, where you have something a bit mid-level. So it's still high level enough so that you don't need to know about the real details, each detail of the robot. But it's not too high level in a way you have enough flexibility so you can use it independently from ARM, and you can easily tinker with it and maybe build something on top of it. And usually when I look at a lot of different open source hardware repositories, this is what seems to be missing. So having something where it's very easy to send motor position all at once, retrieve all the telemetry, or disable motors, so have a clear API that is still giving you access to the full robot, but that is not hiding too much or asking too much. And the last thing where you can improve the interface of your software is to automate repetitive code. As an example, this is what SB3 looked like a while ago. So you needed to manually create an environment, then wrap it in the data structure that you were expecting, and then select the correct policy to pass to your PPU class. And this is a bit annoying because every time you need to run some RL algorithm, you need to repeat the same code again and again. And the idea is here, I can automate a lot of things, at least give good default for the common usage. So if this is used again and again and again, maybe I can automate it so that most of the time you don't need to think about it. And now this is how it looks like. So I could simplify a lot of the code. It's still doing exactly the same thing, and we are not hiding too much either. In the sense that here you can even easily switch between algorithms because you don't need to import a specific policy. It will find the correct policy automatically, given the characteristic you're asking. So that was it for how to improve the interface, how to improve the intuitiveness of the interface. And the last thing I would like to talk about before questions is a design decision that you need to make, which is choosing about modular versus new implementation. As an example, recently I worked on locomotion for a robot, and I tried to find what is the simplest thing that could work, what is the simplest baseline that I can have for reinforcement learning algorithm. And I ended up finding out that just having one oscillator per joint was enough, so having one open loop oscillator, one sinus per joint was already enough in a lot of cases to have something a bit working, and so that I can use it as a base for locomotion. And because I was working with different robots, because I was working also with maybe robots that had different interface with or without joint position interface, I had medium modular code in the sense that I can easily here switch the different environments that I'm using. And I also abstracted away, for instance, the oscillator, and I abstracted away the evaluation. So this code is pretty concise. It's very easy to switch between environments. But for you, if you're new to my code, you will need here to at least read 3-4 files, maybe even read a base class, and to understand what is actually happening. On the other side, I can also provide a single file standalone implementation, so which is what I call minimal implementation, where you have everything. This is the exact same code, and you have everything in only certain line of code, but you only have to look at one file. So it's very transparent of what's happening. So if you want to learn about what's actually happening for you, now it's so much simpler, and you don't need to read 4 files, you don't need to read 1 file, you know exactly what are all the dependencies that you need. And you can easily tinker around. So to go a bit more into what are the pros and cons of modular versus minimal implementation. Another example of modular implementation is the Isaac Lab framework, which will you, once you know about how it works, you can easily define a new task and put your new robot inside it. But usually the entry cost is pretty high. So the nice thing about modular implementation is that you can combine components easily because each component is abstracted away, it's separated. But you need to know where they are. And also because you abstract away those different components, you can also reduce a lot of code duplication. The main issue, and every time I see a software advertised as modular, I'm a bit afraid, is the entry cost. Because when you're working with your own code base that is modular, you know everything about it, you know where everything are, and so for you it's very easy to build something new. But for any new users, well, they will need to read quite a lot of code, and in the case of Isaac Lab, you will need to read probably between 10 to 100 files to actually understand what is happening. And if you want to tweak something and know where something is defined, it might be very annoying to search through the whole code base instead of having to look at only a single file. And coming back to the single file minimal implementation, the idea is here you can have also a minimal number of dependencies. It's really standalone, so it's easier to share. You don't want to cover what your whole code base is doing. Usually you want to cover one big feature of your code base, so you can demonstrate in a single file what's happening. If you provide a single file, well, it's very easy to share with other people because you might not need some private library. It's also much simpler to reproduce because you don't have so many lines of code. And I find it perfect for educational purposes. So when you want to learn about is what happened actually in my case when I wrote some minimal implementation for my open loop oscillator baseline. I actually found a small bug and then I could port it back to my more complex database. The main issue with minimal implementation is because you tend to duplicate a lot of code between the different examples you are provided. It can be a bit hard to manage. So it's usually good for education, but on the mid-term, long-term, you probably should still abstract away some things and have something a bit more. So to conclude, I hope I gave you some tips for creating easy-to-use interface, and I hope that in the future I could use maybe a robot with a very nice, high-quality interface. And I've discussed very quickly about some design decisions that you need to make, notably choosing between having a modular versus a minimal interface or choosing the right abstraction of your API. Thanks for your attention, and I'm happy to take questions.
Thank you very much, Alana. Do we have questions from the audience? In the meantime, I would have one question. If you could pick one of the robots, the open source robots today, even
I have to say I really like the OpenDoc Mini. I might want one at home.
All right. No other question from the audience? Okay, thank you very much, Antonin. So with this, a quick word from Grégoire, and we can have the coffee break of the afternoon.
Yeah, just a quick word. Just giving a short sponsor talk with the scope of Robot Soccer Kit project. Just a word about Robot Soccer Kit. So, Robot Soccer Kit is a project developed by my team. It's a full open source hardware. We are also selling some. That's why I'm sponsoring the workshop. So Robot Soccer Kit is a kit where you build 4 omni-wheel bidirectional robots that are tracked by an external camera. And you can make your own pocket RoboCup competition. So the robots are actually fully custom, so everything is on the GitHub from Robot Soccer Kit. It features a bidirectional wheel, it's 3D printed and laser cut. And there is a front kicker to be able to kick in the ball. The goal of this project is that you can use it for educational purposes, mostly with high school students, for example, but also with starting the beginning of programming lecture. We package a software that is handling the vision. So you can monitor the robot, communicate with the robots, automatically referring the game, and also a simulator and a very high-level Python API. So once you set up the kit, students can start working on very high-level Python API. They have access to the robot location, and they can very quickly take the control of the robots. So here is an example of the simulator with 2 lines of code. You can send the robot to the center of the field and kick. The ball is here, it's a very naive example code, and start building code to make a soccer game. Everything is referred automatically, so since there is a camera monitoring the field, you can detect goals when they are scored, and count for points automatically, and preempt all the robots to set up the game in pause and so on. So we organize a lot of competition in the region. In particular in the scope of RoboCup Junior competition. We organize competition using this kit. We have usually 10 teams in the region working with this kit. It's a very small footprint that you can install in a classroom, for example. So don't hesitate to contact me if you're interested in the
by the 10 minutes or 15 minutes. So, I mean, the next talk will be the 3:30 or 3:35 p.m. So, yeah.
Okay, that should be it. So, thank you very much for coming. Today, I will try to kind of connect with the other presentations and discussions we had throughout this workshop. And let's try to take a step back and look at open source hardware, but not also just the hardware in itself, but in the context of robot learning, which is kind of what is coming up. As one of our speakers said this morning, machine learning has reached robotics and is transforming robotics in various ways, and that also applies to open source hardware. Before I start, we are having a workshop dinner tonight. If you are not registered and would like to join, this is your last chance to come to the dinner. So we have booked for 20 people at Mano de Chef, which is a restaurant nearby here, and there are still a few spots remaining. So if you would like to join, feel free to shoot me an email. There is still room. I will interview first come, first serve. Don't hesitate, it's an opportunity to socialize and have these conversations in a more relaxed way than in this formal setting of the workshop. All right. So I would like to start with a kind of a little historical perspective, but even from my perspective as a young, well, not so young anymore, but a researcher, off the shelf, when we talk about building robots with off-the-shelf components, has improved a lot in the past 10 years. So in 2019, I was working on stair climbing with humanoid robots, and the robots were still expensive at that time. The hardware was not so different from what we have today, but the robots were very expensive, like 400,000 euros. And you really did not want to break them because it was difficult to repair, etc. And from the discussions today, we all understand that open source robots are better for repairing and fixing the robots. And what we did open source at the time was just the software, but not the hardware. Then came essentially Ben Katz, who during his master thesis developed the QDD actuators, quasi-directional actuators. Great master thesis, huge impact on the field in 2018. And so he proposed this design. You already have seen plots of this design today in the workshop. You can also check out his blog. Ben Katz's blog is amazing, not just for robotics, but all kinds of mechanical contraptions. And we talked about 3D actuators this morning with the Berkeley humanoids, for instance. And 3D actuators really changed a lot. When I was a PhD student, we were talking about BLDCs, but they basically stepped up the torque 10 times without a lot of compromise to make. And QDD actuators now, you can actually buy them off the shelf, as we mentioned today, but also if you buy, I'm going to make advertisement for one company because they make open source actuators. And this is MJBot. It's a US-based company, but I've been using them for making the upkey robots that I will talk about later, and they have been truly amazing. And they are fully open source, so you can get the quasi-direct drives, but also you can have just the motor controller board to control any motor you have. The hardware is open source, so you have the mechanical designs, you have the electrical designs. The firmware is open source, so you can, when your motor controller is doing something and you're not sure why, you can go down to the C code and see what's going on, which is really great. And the user-facing software has C++ and Python bindings, so it's fairly easy to use. You can basically, in 10 lines of Python, connect to a motor and control it. And the support done by the company, very professional. There is a Discord channel. If you go there, you will find Josh Piper. He's the main guy between MJBot, and he provides excellent support on Discord. And to the right here, I put you also, for your information, the blog of MJBot, because everything they do, they also document in blog posts. So if you are interested in the thermal models or how to model the magnetic saturation of the motor or these kind of things, not super interesting to me, but if you are interested, these things are fully documented. So I highly recommend this company because they are compatible with open source. So they make business, of course, but everything they do is connected to, is like collaborative. Alright, so let's go back to open source as a software. And so, do you know what open source means? So, if you put your code in a public repository, is it open source software? Who'd say yes? Raise your hand. I put my code on GitHub. Is it open source? Alright, no one raises their hand. Everyone is right. It's not open source if you just put it on GitHub. Do you know why? Who wants to say why it's not open source if you just put it on GitHub? Documentation. No, it's not the documentation. The license. It's the license. You can have documentation as well. Please put documentation as well. It helps a lot. So, okay, so open source has been formally defined with a definition, but the goal is really to create the conditions for collaboration. And if you go back to the definition from 1998, it has actually 10 points. And the first one is a free redistribution. So you can do whatever you want with the software. The points 2 to 4 are about the source code. So that says that you distribute the source code, you can modify the source code, you have the right to modify it. By default, you do not have the right because there is copyright on software, not on hardware. And then points 5 to 10, so actually more than half of the points of the open source definition is to say no discrimination. So you cannot discriminate against the way your software will be used in any way. You cannot say this cannot be a commercial product. If you say non-commercial, then it's not open source because you are restricting what people can do with your software. You cannot say that a group of persons cannot use your software. So if you want to say my software cannot be used by the military, it is not open source, for instance. So this kind of things. So this is documented in the definition. And yeah, it's very important. So basically, when you put an MIT license or an Apache license, you are giving the legal conditions so that people can reuse your software fully. And so now we are roboticists, we make robots. So what does it mean for us if we want to make open source robots? So for the software, okay, this has been taken care of. What about the mechanics? Do we use, so if you look at the current licenses today, we have Creative Commons license, used quite a lot for mechanics. There are also open hardware license, like CERN or TORP. What do you put? For the electronics, how do you share the electronics designs? What kind of license do you put? And then, I'm going to come back to that, but what about the data sets we collect? So we want to do machine learning, we want to learn from real robot data. How do we make sure that people can use our data to train properly new robots? What happens if in our data set there are some dangerous motions and the robots end up executing the dangerous motions? Who's responsible for the execution of these motions? These questions are still open, so not as well defined as for software. So if you use Creative Commons licenses, you may or may not be open source, as a quick aside. So here on the, it's an image I quoted from Wikipedia. On the left-hand side, the CC BY or CC BY SA licenses are open source. That's fine because you don't restrict what people can do. But for instance, on the right-hand side, if you put the non-commercial license, then it is not open source anymore. This is a mistake that many projects make, actually. I'm not blaming anyone, but some robot designs say they are open, and they have a non-commercial condition that is not fully open source. And for hardware, actually, there is an open source hardware definition that has been formalized by the Open Source Hardware Association. I put the links in the slides and you will have access to them. And in this case, hardware is actually a bit more general than mechanics and electronics, but it includes them. So it's anything physical with public source files. So it could be your CAD designs, it can be your electronics design, etc. And if you are a professional like a company or from the industry, they also have a certification program where they help you check that you actually are fully open source on the hardware side. So I will provide links here. And they actually reached out to us also before when we were preparing this workshop. We are not This is not advertisement, they are not paying us, but we learned, I learned a lot from them. Alright, so let's take a look at some open source robots. So for the, I don't know, couple of years, I've been starting to curate a list of open source robots. If you know some open source robots that are not in the list, please add them directly. You can open a PR, it's on GitHub. And it doesn't check much, but it's basically, it's a way to advertise the projects, and for each project, we check the hardware and the software, and we check that there is a license. So, not much. And here I'm going to show you a couple of projects, open source robots projects, to anchor the discussion. One of them is it was made by a YouTuber called James Bruton. It's called RobotX. It's also, incidentally, a robot on my t-shirt. Thanks YouTubers for making branding. It was made in 2018, so quite ahead of its time. And it has been open sourced with GPA for the hardware and GPA for the software. I don't know why, but it's open source. Not really documented. I don't know that it has been reproduced. So it was basically a project to make a YouTube video and get people excited about making the robots. And these videos are also good to show to more and more people that it's not so hard to make the robots. So you have, of course, James Bruton is an expert. He's really good at what he does, but he explains everything, and you can ask questions, etc. So I think that has quite a positive impact for us as scientists, but also for a wider community. At that time, no machine learning yet, and that was a one-off project, so it is not continuously developed. Another example is from the Jet Propulsion Laboratory at NASA, from the same year, 2018, with a battery license. This one is really well documented. So if you go take a look at their documentation, they really went out of their way to make sure that people can reproduce, have all the details on building the electronics, etc. So really inspirational on the dark side. I don't know if it has been reproduced or not. I haven't fully checked. They don't do machine learning, as far as I know, but the project is still active. I checked recently, and they are still committing to it. So that's pretty cool. All right, this one I have a huge bias. Sorry, but I made it. I wanted to put it somewhere. I put it here. This is a wheeled biped robot design using the MJBots actuators I told you about before. And so it has been reproduced, but not on the scale of OpenDuck Mini, not at all. We have basically 5 copies that I know of. And this is an ongoing project where we are integrating new simulators to do machine learning, to do reinforcement learning. And I'm just going to show you a couple of things that people have done with it. So, yeah, so the robot itself comes with the model predictive controller. We also use it kind of in an educational way to try to teach people about the concepts, give them pointers. You know, if they don't know what a model predictive control is, then they can go and check, we show the model, etc. And so there is a teaching aspect to the robot. So you can bring it to class also. That's what we do in Paris when we teach robotics. So when we do the reinforcement learning class, we bring a robot and students can see. Actually, some students take it as a project to train a policy, and during their examination, we make them run the policy on the real robot. And if it crosses the sim to real, they have a bonus because they are really happy. They don't get bonus points, we're not at that stage yet. But it's a good way to motivate the next generation. And then our brother lab from CNRS in Paris built this one. And they worked on getting up, which is another behavior for the robot, where they are combining. They use reinforcement learning as part of the process to design this motion, and then they completed it with model-based in the end. And this is an example. I have other examples. I don't know where I put the video, probably around here. This is also a key-based robot. As you can see, it's not at all the same hardware, but it's the same software. It's open source, so I mean, if the software just assumes a number of motors, so it can run on the number of robots to some extent. So there is this dynamics, which of course we are happy when it happens. When people can just take your project and then they start to do something different with it. That's something, that's something we can seek for open source. Yeah, we'll talk about pros and cons later. And then switching back to open source robots again. More recently there was Open.mini, so 2024, and Antoine told us about it this morning. I was very impressed by the number of reproductions of our project. I didn't know there were so many. This is the first time I see an open source robot project so popular, and they adapted everything. It is really amazing. And we saw Thunderbird as well, so which has an impressive stack for the learning also. I just installed their software. I'm going to try it afterwards. And this project is also still active. So here we can see in these last two the learning side also. When you take the open source project, it's not just the hardware anymore. But if you take Open.mini, there is a playground project. You can just go there and UV run the training script, and it just trains. And I guess for Thunderbird it's the same, but I haven't confirmed it yet. Which I think is something coming up with a new open source robots, the integration with machine learning. All right, I'm not sure how much time I still have, Ento. Is it over yet? It's okay. We'll switch to the discussion. So, yeah, the first time I wrote this slide, I said machine learning is coming, but no, machine learning has come fully to robotics. Okay, and machine learning and reinforcement learning, and including reinforcement learning in there. And so, when we look at open source robots, here is a gallery from the list I mentioned earlier, the list of robots I know of, and it's a public list, so you can add. Here is a list that's filtering out only the robots that have been trained by reinforcement learning using Sim2Real. And here I filtered out the robots trained from real data. From what I saw this morning, I need to add back Toddlerbot, but that would be the first one in the list to make it, in learning a policy trained from real data. And I think this is, in my opinion, feel free to contradict me and discuss this later, but I think this is what the next front is, that we don't just do Sim2Real, but we actually train from real robot data that's collected, either from one robot, if there is enough, or collectively. And I'm not the only one to think this, because, for instance, Hugging Face, so the company which we talked about earlier today, has this project called LeRobot, which is a robot interface library combined with a dataset collection. And so on the right here, you have numbers for the size of the dataset collected by LeRobot. And basically what happens, if I understood correctly, I haven't checked fully the code, but from what I understand, if you take an arm, so LeRobot has interfaces for, I don't know, 5 or 6 robots, maybe Antoine, I don't know, like the Amazing Hand, I think is in there. Aloha, the SO100, etc. So yeah, so you take the SO100, you connect it to the USB of your computer, and then you run the LeRobot software. By default, it is going to collect data and upload it to the hub. And I think if you want to opt out, you have to tell the software that don't upload, otherwise by default it will just share with everyone. So that's one way to collect the data. Then the curve goes nicely up. But I think the story is only the beginning, because then you have the question of curating the data. Everyone can put into this pool. So what if you get corrupted data? What if you get a massive amount of data when the robot just does nothing, etc., etc. So I'm not sure if there is some filtering already in place. Probably, I don't know. But if the issue hasn't happened yet, it might happen in the future. And so, yeah, to me these questions are currently in the air, and probably the next open source definition might be an open data definition for robotics, for instance. I was starting to add to this slide, but I didn't mention that there are already projects of big data sets, like the OpenX and Bot data set. I think some of you have worked on it. think you are the OpenX embodiment paper.
Yes.
Yes, exactly. We can talk about it. So there are many big data sets coming up, and I think this is one trend where interesting things will happen. And of course, Professor Ogata this morning mentioned the Aero open data set, so I think also these discussions are happening right now. And finally, so that's the data set question. And so finally, I wanted to reflect with you on, why do we make open source robots, basically? So, okay, it's cool to make open source robots. No discussing that. But then depending on who you are, there are actually pros and cons of doing this. So as an individual, it's great. Like, you don't only make a project, but you get some visibility. You can get spontaneous collaboration from other people in the world that find it cool. It's not the same incentives as a laboratory, for instance. So we all mentioned today in our laboratories, what we like about open source robots is that we own the full stack. I'm not the full stack. We mentioned also some, like the actuators, the servo motor actuators that don't have open source firmware. So sometimes we don't have the full stack, but the more we own, the more we can change, and thus we can do some research. So that's good for us. And for companies also, so there is a cool factor to it. It looks good, of course, when you contribute back to open source, and it can be a way to collect data from the community, etc. But on the minus side, as individuals, you can see these projects, they come and go. Some projects pop up, get some visibility, they look cool, and then it stops because people go somewhere else. And that's okay, that's what happens in open source. For laboratories, there is a risk of divesting from research. That's a risk you know in robotics. Basically, when you start doing engineering full-time, and then people just want to fix problems, okay, fair enough, but you need to keep an eye on the research, on trying new things that the others are not doing, etc. But doing open source can put an extra pressure, because then it's public. So you get the pressure from the community, people saying, oh, this doesn't work, and it's a public-facing thing. So for laboratories, also, this can be an extra pressure. And for companies, it's the same. It's an extra pressure. You have to devote some engineers to develop that software, and then it's not like, if you make a mistake and it's internal, it's not the same as you make a mistake and then it's a software that's downloaded 50,000 times a day or 100,000 times a day, and then your mistake is propagated everywhere through the chain. So yeah, I wanted to open this discussion with you. Basically, should we make open source robots? How do we make them? With these thoughts, I will thank you very much for your attention. Take any question, and also ask our panel speakers to stand up and slowly come to the stage so that we segue into an open discussion together. Thank you very much.
If you have any question for Stefan, please ask by using the microphone. If not, we will simply go to the discussion, panel discussion with some of the invited talkers. Any questions? Okay, so please come to the here to Thomas and all people who did the invited talk, the meeting here. Is there another? Yeah.
All right, thank you very much. Thank you to our panelists for accepting to come and have this discussion together. So I just took some notes during your respective talks today, and I want to throw some questions at you Feel free to answer freely. There is no, I mean, it's less formal now. It's mostly a panel discussion. The first thing I wanted to ask, what do you think about the, let me see. So, how much do you think that, as scientists, how much do you think we should invest into the software maintenance of our open source projects? Like, do you think we should write good documentation, or do you think we should leave the documentation to someone else? What are your thoughts on how much the scientists should do when they release their open source software?
Actually, it's not only in Japan. So there are some projects for the related middleware or also such as open source software, but always have the difficulty writing paper. So just maintenance, keep the maintenance, and try to open that. How can we publish such as original works? That is so especially young generations always make such kind of difficulty. So to keeping the maintenance over to keeping open always has such kind of difficulty. But I expect it to continue such kind of activity, connecting such kind of different kind of field, especially the robotics people use so work on many focus, just focus on hardware parts. So the maintenance will take a long time. But so at the same time, I expect them notice to the so especially from the people in Japan. So notice find such an open culture in the AI people. Yes. So how they are using so very specific cross world in Japan, but to keeping the continuous such a maintenance for the open software such as middleware. So how to make the connections. That is now so yeah, these workshops are really surprising. Everyone's it seems to be natural to making the connection AI but usually these two worlds are very separated in mechanical engineering or something like that. So that people is not so familiar with open hardware, right? So yeah, so keeping the maintenance is always hard, but to keep the connection. That's very important activity. That's my point.
Yes, thank you very much.
So maybe on my side, so it's very challenging, both software but also hardware, to properly document to enable productivity. In the same time, if we want to call it an open source, open hardware project, we don't have choice to ask ourselves those questions. We have to properly document, I think, otherwise we lose people time and there's no benefits to that. In the same time, I think we have to sometimes let go projects that become old or maybe not all project needs to be supported for X amount of time and it's always evolving and some project could have been built on top of ours and replace and become the new standard. So that's a way also to allow us to be okay with the fact that we don't have to maintain for life X number of projects.
Sure.
Yeah, so you're asking about an researcher's role of such an open hardware, right?
Yes.
So in my opinion, so we have so many stages. So as you know, Linux is a very good open source software and operating system. And as you know, the laws is also. So many kind of software is now in public. And they growing up in an early stage, researchers and individuals have an important role to develop. And also the users is also best people working for that area. But the second stage is growing up in open community and expanded all over the world, and there are many contributors involved into the open source system. And also then laws and Linux, so many kind of de facto standards. So it should be that you see that the standardization is involved many people. So many people are thinking about what is standard. So I mean that common something, and then competitive is a company working for such a competitive area. So it's a different stages. One is an early one, and the second stage, and then how to say, industrial stage or something. I don't know in the English name, but it is very different. So researchers are working for such a early stage. So in open hardware of robot is in a very early stage. So we should make such a good community to expand to the industrial use. So it is a good session. I think this is a very good session. So I hope that you give a definition of the open hardware here, and I support an risk assessment. So it is I think that right now is a very early stage of the robots and the machine learning and the AI. So this discussion is very good, I think.
Thank you very much for your feedback.
And yes,
go ahead.
My point of view, it depends really as well. So the original question was, is it the job of scientists and researchers to maintain open source repository?
Right.
And it really depends on the structure of the team. I am from a small team, so we don't have a currently permanent engineer, for example. So it really depends on the structure of the team. And also on the background of the researchers themselves, because maintaining and documenting open source project properly is a really specific job. So you need to know how to do it properly. And if you have the background and if you feel like there is some useful tool you can develop and useful project you can maintain, I think it's totally in the scope of a researcher to do so. It's public money, it's public code, public interest. So for me, yes, Karen.
Nice. Thank you very much. Yeah. Maybe a follow-up question. Based on your feedback, you mentioned that I think we have a consensus that there is a wave coming up of open hardware or open data. What are the risks that you see today for this new wave that is coming up? Do you have some risks in mind, like a lot of open hardware comes up and that creates a problem, or maybe a lot of open data comes up, open robots data comes up, and it's problematic?
I think one risk is that it's a very, very fun activity to do, build a robot from scratch, and then it's maybe not as effective that everybody does exactly the same stuff in their way. It's difficult to build the information. So I guess this can be a risk to be compared with all the very good advantages to have many people training themselves to do so. So maybe it's not. Maybe it is a risk that we want to have, but so maybe that's one.
Yep.
Here is in our association, robot association, we already started collecting data, but now just focus on the task at home, daily work. So, but maybe if we make a foundation model with collaborating some target companies, they prepare some specific data. So we need to make some kind of framework for management, which part of the data is made, so should we keep or should we go? So, but still not 100%. There's such kind of bind out there now. So maybe we need to discuss with not only the engineer, maybe the more other researchers from the social scientists or something like this. Maybe some
don't collect such data, but we use the machine learning system, machine learning to apply our robot to eating chicken nugget or something like that. So I'm not sure about 10 decades later, maybe some of the data is open source, and this is a common level, and a special level is different data to keep the manufacturing or sales management, something like that. And also, we think about such a data is how to say, resolution is different, I think. So, as you know, you think about digital camera has data. So 30 years ago, then we had the first digital camera that is 0.1 million pixels, but right now the 5 million pixels, something like that. So resolution is very different. So maybe AI data is also different from the right now and then 10 decade, 1 decade later or something like that. So how to say it is difficult to talk about data and machine learning and physical AI, something like that. So I think it's difficult to talk about it right now.
Okay, I think the risk of open data sets is that effort is likely to be very small compared with the effort made by private companies. In particular for imitation learning, where data is very expensive to get. And I think publicly available models and data sets is likely to always be behind what private companies can achieve, actually. Making the first company to invest a lot of money into building huge data sets, some kind of a big trust that we can't compete against. So the issue is that maybe it's not too much for the way.
Not enough.
Not enough, yes.
That's very interesting. Actually, I want to start thinking about it. I haven't asked, but do people from the audience also have questions for our panelists? Don't hesitate to step up. I mean, this is an interactive session. It's not as formal as a workshop, so it's not just presentations, but we are having a conversation. All together today. I can follow. Yeah. Go ahead. Yes.
So thank you for the discussion. I was wondering, maybe, so there is this whole CC by non-commercial, for instance, and with the availability of all these data sets, do you think maybe the community should think about some kind of ethical criteria on the use of available data sets? Because we could imagine, I don't know, like a CC by non-military application, or if you I don't know if you provide tons of drone data sets, because drones humans currently use a lot. You could imagine maybe that some groups would use that just to train their own stuff. So yeah, like let's say an ethical aspect to the use of the community data sets, let's say.
Yes. What do our panelists think about it? Yeah.
So as an example, I recently learned that Ukrainian soldiers use drones to attack planes in Russia. Well, they use heavily RWPilot, which is open source flight controller for quadcopters, and it's very well stated in the documentation that any use for military or application where you want to destroy stuff are totally forbidden from the license. But will them? Well, no, they just don't care because they need it, they take it, and they will slay it off. And so I'm very skeptical on the rules we can put. Maybe we can fight 10 years later legally against misuse of our software, but just licensing is not a solution for ethical problems, I think.
Actually, the animation problems, especially almost impossible to avoid that if once you open the data, even some of the works in a home daily works, some of the tasks could be easy to use such kind of target tasks. So now that we just say something, I think we should say something to open data over hardware, how such kind of solution we should, what that kind of target is, so we should use for something. But yes, that is just a policy. Maybe once the technology or data is open, that is very hard to control at all. That's my thinking, kind of thinking.
Thank you very much. It's true that I don't know if there would be an ideal solution, but yeah, it's a bit hard to.
Yeah, thank you for the question. I mean, I agree. It's to the project. Go ahead. Yeah.
Okay. So I have a question related to open hardware, and right now with data-driven models being a trend in the world, I believe that right now open hardware is underrated in the sense of that there's not how to say, like, we are not able to compare how good is the hardware that we have developed over different already open hardware solutions. And that's why maybe some researchers refrain from doing open hardware and they just work with commercialized robotics. So far I've been also in Japan for almost 8 years participating in RoboCup at Home League. And especially in the open platform league, where most of the teams, they develop their own platform and participate on those household tasks. The number of teams participating in this league is being declined years by years. Maybe one of the most recent is that they are not being able to find a research merit for this field, and they just focus in the software. Do you think that it's possible to create something to evaluate those kind of platforms depending on the field that it's going to be used?
So your question is about the evaluation of the open hardware we make.
Exactly.
So if I rephrase, when we make open hardware, we are kind of isolating ourselves from the rest of the community because our robot is unique. And your question is, what are the ways in which we could go beyond that? Keep making open hardware, but still continue our research.
And as you say, competition is maybe part of the answer as well, because RoboCup is a good evaluation. For example, you just face opponents, you score points, so it's a good way to benchmark. But there are some projects as well for benchmarking robots. In particular, you get some qualification with a set of tasks. I don't know how common and spread it is, but I saw some project like that already. I think that's a good idea overall. So you get some kind of standard test. For example, you have a category like humanoid robots, and you have a list of benchmarks, and you get some kind of certificate of what the platform is able to do. That would be a solution, maybe.
My opinion. So there's many different types of ways to evaluate the hardware. So specification, what costs, how many freedom, something like that. But currently very interesting that in the slide mentioned, so how it can be combined with machine learning. Now it's many people interested. So that is a very new viewpoint for the open source open hardware. Before the machine learning, there are many open hardware that I mentioned, but now everyone wants to use a really interesting point. But yeah, it's still very hard. First is so if it's just winds and such a convection, so some parts should be used machine learning, but some parts should not be used machine learning. So maybe it depends on the final goals. Yes. But now everyone seems to be interested in such a viewpoint. How machine learning can be used hardware. That is a common sense in this workshop. So not clear answer. That's a common sense.
Thank you very much. Yeah. Do you have any comments? Yeah, go ahead.
So, thank you for the very good question. So, I think, so Professor Ogata said various evaluation, and one is, in my opinion, so one is how to keep the parts to develop the sort of open hardware. In my company, making the open source for the education, and one point to keep the how to say product life. So if we choose discontinued parts, so open hardware is not dead. So if the 1 year, 2 year, or something like that, and open software, you can change the code according to the version. But the hardware is very difficult to replace with it. So one evaluation point is on the life of the product. Yeah. And also the second is on the information about that. Because we restricted for the researchers or the students. So they need information about how to use these robots or how to use these robot parts and how to apply their theory or method or something like that to the robot. So they need the information to use on research purpose. So our product is two versions, one in the lifetime and the one in the information.
On my side, I would say that the question is a bit difficult because for any different robot, even commercial robots, it's difficult to compare two robots. There is no one better than the other. There is a lot of infinite criteria to consider. And I think you can totally compare an open hardware robot, maybe even more easily than a commercial robot because you are able to build it and to know exactly every aspect of it. So we cannot cheat when we say what is inside an open robot.
So let's keep doing open hardware robots as well, to some extent. The time has come. Thank you very much to our panelists for answering the questions. And thank you very much to the audience for asking these questions. This is super interesting. So now we will be switching to the award ceremony. And with this, I will leave the floor to Kento.
So, yeah, trusted open source hardware workshop hours. So maybe the meeting will come soon, so please be very soon.
Guys seen the recently actually during the demos? Okay, well if you haven't, here is one.
So I have some notification about the hours. So for hours, so wow, 9 but actually there is two sponsors, the RSK, Sakaki, and also Hanging Face. So we can only give the 2 each minute. So therefore we selected the 2 best poster hours, which each receive each mini, and the 1 best open source hardware hour, which cannot get the Okay, so the first one, so let's, oh my god, okay. Best poster hour is very high frequency interpolation for direct control. So any author from here? No. Okay, come.
Well, with this, we want to thank you all very much for attending today and contributing to the discussion. For those of you who want to continue the discussion even further and in a more relaxed, beverage-enhanced environments, we also have the dinner starting at 7 p.m. Feel free to join. So again, thank you very much, everybody. Have a nice conference. For those who want, we can take a group picture. Come on, on stage. Come, bring the head, bring the Ruchini. Oh yeah.
Come on stage.
Thank you.
Thank you.
Thank you for coming.